In the vast, silent theater of the cosmos, a question echoes louder than any explosion of a dying star. What is this place we call the universe, and why does it behave in ways that defy our understanding of reality? For centuries, humanity has stared into the night sky, mapping constellations, charting the paths of planets, and dreaming of distant worlds. But with every answer we uncover, 1,000 new mysteries emerge from the shadows of space. Time, we once thought, marched forward in a straight, unchangeable line. But Einstein shattered that notion, revealing that time can bend, twist, and even slow down depending on your speed or proximity to a massive object. Space, once assumed to be an empty void, is now understood to be a seething, dynamic fabric called space-time, capable of warping under the influence of gravity, giving rise to strange phenomena like black holes, gravitational waves, and the bending of light itself. Yet even with these profound revelations, we've only just scratched the surface of cosmic truth. Imagine a force so powerful and so vast that it comprises nearly 70% of the universe, yet remains invisible and undetectable to every instrument we've built. This is dark energy, a mysterious pressure pushing galaxies away from each other at accelerating speeds, counteracting gravity, and defying all known physics. Alongside it lurks dark matter, an unseen substance that makes up most of the mass in the universe, shaping galaxies and anchoring cosmic structures, yet refuses to interact with light or ordinary matter in any measurable way. These components together form over 95% of everything that exists, leaving the stars, planets, and atoms we're familiar with as mere crumbs of reality. But the mystery deepens when we consider black holes, the cosmic beasts that devour matter and light, warping space-time to the extreme and forming event horizons beyond which no information escapes. Scientists once thought black holes were endpoints, dead ends in the cosmic script. But now, theories like Hawking radiation suggest they can evaporate, slowly leaking energy over time. And some even propose they may be portals to other universes or dimensions. This leads us to the radical idea of white holes, theoretical opposites of black holes that expel matter rather than consume it, potentially functioning as exits to the same entrances black holes provide could. These structures form an interdimensional highway threading through the fabric of reality. If that possibility doesn't break your brain, consider the multiverse theory, which posits that our universe may be just one bubble in an infinite cosmic foam, each universe with its own laws of physics, particles, and even versions of you. Quantum mechanics, the baffling theory that governs the behavior of the very small, supports this kind of thinking. Particles can exist in multiple states at once, only settling into one when observed, suggesting that observation itself plays a role in shaping reality, and hinting at the possibility that every quantum event could spawn a new universe. Then there is the enigma of consciousness. Is it merely the product of neurons firing in the brain? Or is it something more fundamental, something that weaves into the very structure of the cosmos? Some physicists argue that consciousness might play a role in collapsing quantum states, suggesting that the act of observation isn't just a passive event, but a participatory one, and that perhaps the universe only truly exists because there's something here to witness it. This loops us back to the age-old question of why the universe seems fine-tuned for life. Physical constants such as the strength of gravity, the charge of an electron, and the rate of cosmic expansion are balanced so precisely that if they were even slightly different, atoms wouldn't form, stars wouldn't shine, and life as we know it would be impossible. Is this sheer coincidence, evidence of design, or simply one possibility among infinite others in the multiverse, where we just happen to live in a universe that works because we're here to ask about it? These aren't just philosophical musings, they're questions at the bleeding edge of physics, cosmology, and metaphysics. The James Webb Space Telescope, peering deeper into the early universe than ever before, has already upended theories by spotting galaxies too old and massive to fit our current models, suggesting that something fundamental about our understanding of cosmic evolution is wrong or incomplete. And yet, the more we see, the more the universe seems to hide, as if it's keeping its deepest secrets just beyond our grasp, revealing them only when we're readier, when we're willing to break the rules we thought were sacred. The cosmic microwave background, the afterglow of the Big Bang. whispers to us in patterns and fluctuations, possibly hinting at collisions with other universes or anomalies in the structure of our own, inviting us to listen more carefully, to look more deeply, and to question more boldly. At the heart of all this is the Fermi paradox. With billions of potentially habitable planets in our galaxy alone, why haven't we detected any signs of intelligent life? Are we the first, the last, or the only ones? Perhaps the great filter lies ahead of us. A barrier no civilization can pass: nuclear war, environmental collapse, or technological self-destruction. Or perhaps it lies behind us, and we're among the rare few who made it through. Or maybe, just maybe, we're being watched, studied by civilizations so advanced they operate in ways we cannot comprehend, hidden from us not because they fear us, but because they follow a cosmic code of silence, waiting for us to evolve, to unify, to transcend. Every discovery we make, every telescope we launch, every equation we refine, brings us closer to understanding not just the mechanics of the universe, but the narrative, the why, not just the how. And that narrative is far stranger, more beautiful, and more terrifying than we ever imagined. In this unfolding story, we are both characters and authors, explorers and the explored, asking questions that pierce the veil of time and space. What lies at the center of a black hole? Are we alone in the cosmos, or surrounded by civilizations that choose silence over contact? Is our universe a simulation, a biological entity, or a dream being dreamt by something far greater than ourselves? The answers may not come easily or quickly, but the pursuit itself reshapes us, challenging our minds, expanding our awareness, and elevating our role in the grand cosmic symphony. This is not just science, it is philosophy, poetry, and prophecy, written in the language of light and gravity, radiation and matter, across the boundless canvas of space-time. And somewhere in the darkness between the galaxies, the answers are waiting. For most of human history, the universe was not a concept measured in billions of galaxies or light years, but a mysterious dome of stars revolving around a motionless Earth. Our ancestors looked up at the night sky and saw patterns: Orion chasing the Pleiades, the slow march of Venus across the heaven sand. From these they wove myths and calendars, religions and rituals. The earliest astronomers, from the Babylonians to the Maya, mapped the skies with astonishing precision, predicting eclipses and solstices without telescopes, driven by wonder, fear, and a need to understand their place in the cosmos. Yet their models, though sophisticated, were rooted in geocentrism, the belief that Earth was the center of all things, and the stars were fixed lights in a crystalline sphere. This worldview dominated for millennia, reinforced by Aristotle's physics and Ptolemy's complex system of epicycles, which tried to account for the strange motions of planets. It wasn't until the 16th century that a quiet revolution began. Sparked by the Polish astronomer Nicolaus Copernicus, he dared to propose a heliocentric model, where Earth and the other planets orbited the Sun. Though Copernicus's model was mathematically simpler, it wasn't immediately accepted. Challenging Earth's central position wasn't just a scientific controversy, was a philosophical and theological one. But then came Galileo Galilei, who turned a primitive telescope toward the heavens and saw Jupiter's moons orbiting their planet, the phases of Venus, and craters on the moon, evidence that not everything revolved around Earth, and that the heavens were not perfect and unchanging as the ancients had believed. Galileo's findings, along with Johannes Kepler's mathematical laws of planetary motion and Isaac Newton's laws of gravity and motion, formed the foundation of classical mechanics and offered the first universal framework for understanding celestial movement. With Newton's Principia Mathematica in 1687, the universe became a machine, governed by laws, where apples fell and planets orbited for the same reason. This shift marked the beginning of modern cosmology, though the universe still seemed static and eternal. For centuries after Newton, scientists believed in a clockwork universe that had no beginning or end, simply governed by immutable rules. But the 20th century would shatter those assumptions. In 1915, Albert Einstein published his general theory of relativity, fundamentally redefining gravity not as a force, but as a curvature in spacetime caused by mass and energy. This elegant, complex theory predicted phenomena like the bending of light by gravity, gravitational time dilation, and most radically, the possibility that the universe itself could be dynamic expanding or contracting. Just a few years later, in the 1920s, astronomer Edwin Hubble used the newly built Hooker telescope to observe distant galaxies and discovered that they were moving away from us. Not only that, but the farther away a galaxy was, the faster it seemed to be receding. This relationship, now called Hubble's law, confirmed that the universe was expanding, a revelation that led directly to the Big Bang Theory. The idea that the universe had a beginning, a moment of creation from a singularity, was revolutionary. Georges Lemaitre, a Belgian priest and physicist, was one of the first to propose it, suggesting that all matter once existed in a single point he called the primeval atom. Initially resisted by many, including Einstein, the theory gained traction when physicists Arno Penzias and Robert Wilson accidentally discovered the cosmic microwave background radiation in 1965. This faint glow of heat, evenly distributed across the sky, was the smoking gun, the afterglow of the Big Bang, confirming that the universe began in a hot, dense state and has been cooling ever since. Over time, our models of the universe grew in complexity and detail. The Big Bang Theory, enriched by concepts like cosmic inflation, dark matter, and dark energy, became the dominant cosmological framework. Inflation proposed that the universe expanded faster than the speed of light in the first fractions of a second after the Big Bang, explaining the uniformity of the cosmic microwave background. Dark matter, first hinted at by Fritz Zwicky in the 1930s, and confirmed by the rotational curves of galaxies, added another layer of mystery mass that exerts gravitational pull but doesn't emit light. Then, in 1998, observations of distant supernovae led to the shocking discovery that the universe's expansion is accelerating, not slowing down as expected. This was attributed to an unknown force dubbed dark energy, which now appears to comprise about 70% of the total energy content of the universe. Alongside these theoretical breakthroughs, the technological advancements of the space age transformed our ability to explore and understand the cosmos. The launch of Sputnik in 1957 by the Soviet Union began a new era, quickly followed by Yuri Gagarin's historic orbit of Earth in 1961 and the Apollo 11 moon landing in 1969, which marked the first time humans set foot on another celestial body. These milestones captured the imagination of billions and demonstrated humanity's capacity to reach beyond Earth. But perhaps even more transformative than manned spaceflight were the robotic missions and space telescopes that followed. The Voyager probes, launched in the late 1970s, gave us the first close-up views of the outer planets and are now drifting through interstellar space, carrying the golden recorder message to the cosmos. The Hubble Space Telescope, launched in 1990, revolutionized astronomy by capturing images of galaxies billions of light years away, observing the birth and death of stars, and refining the rate of cosmic expansion. More recently, the James Webb Space Telescope has begun to peer even deeper into the early universe, offering glimpses of galaxies that formed just a few 100 million years after the Big Bang, challenging our models of cosmic evolution. These achievements have deepened our understanding of the observable universe, the portion of the cosmos we can detect from Earth. Light travels at a finite speed, and because the universe is 13.8 billion years old, we can only see as far as light has had time to travel. However, due to the expansion of space itself, the observable universe is far larger than 13.8 billion light-years in radius. In fact, we can observe galaxies as far as 46.5 billion light-years away, placing the diameter of the observable universe at about 93 billion light-years. This sphere represents not a boundary of existence, but a limit of visibility, a horizon, beyond which light has not yet reached us. It's important to understand that the observable universe is not all there is. The cosmos may extend infinitely beyond this horizon, with untold galaxies, structures, and perhaps even laws of physics unknown to us. Throughout history, each breakthrough in our understanding of the universe has shifted our perception of ourselves, from geocentrism to heliocentrism, from a static cosmos to an expanding one, from a visible universe of stars to a dark universe dominated by unseen matter and energy. We have continually been humbled and awed. The journey has been marked by bold ideas, experimental verification, and the relentless human drive to understand the cosmos. It is a journey far from over. As we stand on the shoulders of those who gazed up in wonder thousands of years ago, we now send machines to Mars, plan missions to Europa and Titan, detect gravitational waves rippling through space-time, and scan the skies for biosignatures on exoplanets. We build particle accelerators to recreate the conditions of the early universe, and we model scenarios where time itself may have emerged from quantum fluctuations. The concept of the observable universe is just one piece of a far grander puzzle, a reminder of both our limitations and our potential. In the centuries to come, humanity may unlock even deeper truths about the nature of reality, discovering the fundamental particles that underlie matter and energy, decoding the nature of dark energy, unraveling the geometry of space-time, or perhaps even transcending our biological form to explore the cosmos in ways we cannot yet imagine. But for now, the historical arc of cosmology teaches us that knowledge grows not only through answers, but through better questions. Every era believed it had the right model of the universe until new observations shattered the illusion. It is this humility before the cosmos, this willingness to revise our understanding in light of new evidence, that defines the scientific spirit. We are the latest chapter in a story billions of years old, unfolding on a fragile world orbiting a medium-sized star in a galaxy among trillions. And yet, we are the only ones we know of who ask why. That simple act of wondering may be the most powerful force in the universe. When you look up at the night sky, do you ever feel that tiny pull in your chest, the feeling that something unimaginably vast is out there, far beyond what you can see or understand? That emotion, hard to define yet deeply familiar, is one of the most ancient and profound human experiences. It's the quiet ache of curiosity, the thrill of possibility, the humility of realizing how small we are, and yet how strange and beautiful it is that we can ask the question at all. What is this universe? And why does it matter to me? We live our daily lives caught in the routines of work, relationships, and survival, often focused on the here and now. But the universe, the real one, not just the stars we see on a clear night, isn't just a backdrop to our lives. It is our origin story, our cradle, and possibly our future. Every atom in your body was forged in the heart of a dying star. The iron in your blood, the calcium in your bones, the oxygen in your lungs, all of it was once part of something that exploded in a supernova millions or even billions of years ago. You are, in the most literal sense, a child of the cosmos. And yet, the universe is not a warm, welcoming place. It is cold, vast, and mostly empty. It is a void of darkness, punctuated by fleeting bursts of light, chaotic collisions, and silent, slow-moving catastrophes. It is indifferent to your hopes, your fears, your dreams, and therein lies the emotional paradox that makes space so hauntingly powerful. How can something so impersonal stir such deep feelings of awe, loneliness, wonder, and meaning? We care about the universe because in it we see ourselves. We see our fragility and our resilience, our insignificance and our potential. To stand beneath a sky full of stars and feel the weight of distance and time pressing down on you is not a weakness. It's a reminder that you are alive in a story far larger than anything you can imagine. And for many people, that realization is terrifying. The idea that Earth is just one rock among billions, circling one star among trillions, in one galaxy among uncountable others, makes life feel small and maybe even pointless. Why strive? Why love? Why suffer? Why do anything if the universe doesn't care and no one out there is listening? This is the existential dread of the cosmos, the fear that we are utterly alone, that there is no grand design, and that the lights will one day simply go out. But that same realization can be flipped on its head. If we are alone, then how precious does that make our existence? If consciousness is rare, then every thought, every act of kindness, every shared moment of beauty becomes infinitely valuable. The silence of the cosmos is not a curse, it's a blank canvas. We get to choose what meaning we create. We are the storytellers, the record keepers, the observers. Without us, the universe is just physics. With us, It becomes art, philosophy, and music. It becomes something that can be known and felt. When we stare into the cosmic void, we are also staring into our future. Our sun will one day burn out. Our planet will be swallowed or frozen. Every civilization, no matter how advanced, must confront the brutal laws of entropy and decay. But this inevitability drives us to explore, to reach beyond, to imagine worlds beyond death. The first humans to launch a spacecraft, to walk on the moon, to send robotic eyes to the edges of the solar system, they didn't do it just to gather data. They did it because of an almost spiritual hunger to connect with something greater than themselves. That same hunger lives in you. Maybe you felt it when watching a rocket launch, or reading about a distant exoplanet that might have oceans like Earth, or hearing the haunting sound of a black hole's gravitational wave translated into audio. These moments stir something primal, a blend of hope and sadness, because they touch the part of us that wants to believe there's more to discover, more to become, more to feel. The universe does not owe us meaning, but it gives us the raw materials to create it, and in doing so, it hands us a mirror. When we study the stars, we are also studying ourselves. Our ability to ask questions about time, origin, and fate is not a flaw, it's our greatest gift. People should care about space not because it will give us all the answers, but because the questions it raises help us live more fully here and now. What is life? And how rare is it? Could we share this universe with other forms of consciousness? What happens when a civilization survives long enough to transcend its planetary limits? These are not just technical puzzles, they are deeply human dilemmas. They force us to reflect on how we treat our planet, our fellow humans, our own potential. The overview affect a psychological shift experienced by astronauts when viewing Earth from space shows us that seeing our world from a cosmic perspective creates empathy, clarity, and a renewed sense of purpose. Suddenly, there are no borders, no politics, no division, just one fragile world in an ocean of darkness, alive and aware. That feeling is not reserved for astronauts alone. Anyone can experience it with enough curiosity and wonder. To care about the cosmos is to embrace both the terror and the beauty of not knowing. It is to hold uncertainty not as a threat, but as a frontier. It is to wake up in the morning knowing you are part of a 13.8 billion year story, that your atoms are ancient, and your ideas might be the newest phenomenon in the known universe. Imagine what it means that a species of primates developed language, science, and self-awareness, then turned their eyes outward to understand the very structure of existence. This is not a trivial achievement, it is one of the rarest things we know to exist. And if our civilization were to disappear tomorrow, what would be lost is not just our cities and our technologies, but our questions, our dreams, our cosmic reach. That loss would be tragic, not because the universe would notice, but because we would have silenced one of the few voices capable of asking, why is there something instead of nothing? Wonder and fear go hand in hand when we confront the universe. The wonder is intoxicating, the idea that there might be planets with purple skies and alien oceans, that time might behave differently near a black hole, that wormholes could bend space itself. But the fear is just as potent, that we may never reach those worlds, that our species might self-destruct before we ever leave Earth, that the silence we hear in space is not because others aren't there but because they didn't survive. These dual emotions drive our greatest stories. From myths of gods riding the stars to modern sagas of astronauts crossing impossible distances. They remind us that exploration isn't just a physical act, it's an emotional and psychological journey. The unknown is always frightening, but it's also where all growth begins. And that's why the universe matters. Not because it promises us comfort or safety, but because it dares us to be more than we are. It whispers possibilities through radio waves and spectral lines, through distant signals and gravitational echoes. It challenges our arrogance while also expanding our compassion. It reminds us that we are not the center of all things, and yet, in our awareness of that truth, we might become the most meaningful part of it. You don't have to be a physicist to care about the cosmos. You just have to be someone who's ever asked a big question. What happens when I die? What's the purpose of life? Are we alone? These questions aren't side effects of science. They are the heartbeat of it. And the cosmos, in all its strangeness and silence, is where we look when we're brave enough to admit we don't know. Perhaps the most powerful emotional reason to care about the universe is the possibility that our story isn't over. That we are not just dust in the wind, but the beginning of something extraordinary. That a child born today might one day walk on Mars, or help build a telescope powerful enough to see the first stars form, or make contact with a distant civilization. These aren't just dreams, they are goals, ambitions, futures that grow more real with every discovery. The universe isn't cold and empty, it's waiting for someone to understand it, to experience it, to give it meaning. And maybe that someone is you. Maybe the reason you've always been drawn to the stars is because, in some deep way, you already belong to them. Maybe your story has always been bigger than one planet, one lifetime, one moment. Maybe, just maybe, the universe cares too, not in the way we understand emotion, but in the simple fact that it made you. Out of hydrogen and gravity and time, it made a being who could feel awe, who could seek truth, who could love and wonder and cry beneath the stars. And that, more than any equation or discovery, might be the greatest mystery of all. Have you ever wondered what it truly means to exist in a universe so vast that entire galaxies can vanish from our view? Not because they cease to be, but because space itself is expanding faster than light? Have you paused to consider how each new discovery about the cosmos doesn't just tell us more about the stars, but reshapes the very framework through which we understand our lives, our relationships, our histories, and even our futures? These aren't idle thoughts. These are the cracks in the surface of ordinary life. The moments when the questions come rushing in: where are we, really? Why is there something rather than nothing? What does it mean that we are capable of asking at all? These mysteries aren't distant, irrelevant puzzles. They affect the way we think about our place in everything. When science tells us that time is not absolute, that space can bend, and that particles can exist in multiple states until observed, it challenges the very foundation of what we consider real. It forces us to ask, if time is flexible, how do we measure a moment? If reality depends on observation, what role does consciousness play in shaping the universe? These are not questions for scientists alone. They belong to all of us. If you're human, you're qualified to ask the biggest questions imaginable. And now, more than ever, we need people to care. The more we learn about the universe, the more we realize how much we don't know. What lies inside a black hole? Are there more dimensions than the ones we experience? Is our universe one of many, floating in a cosmic sea of alternate realities with different laws of physics? The answers could fundamentally alter not only our scientific understanding, but our philosophical and emotional ones. If there are infinite universes, does that mean every possibility exists somewhere? A version of you who made a different choice, took a different path, lived a different life? If the laws of physics can be different elsewhere, does that mean consciousness, life, and even time itself can exist in forms we can't begin to imagine? Imagine a discovery so profound it redefines our species overnight. What if we detect a radio signal from another civilization? How would that change our understanding of intelligence, of our uniqueness, of our destiny? Would we panic, unite, evolve? Would our priorities change? Or what if we found definitive evidence that the universe is a simulation, a programmed construct within a greater reality? How would that reshape the way we approach morality, freedom, and purpose? These scenarios aren't just science fiction. They are plausible futures being explored by leading physicists, technologists, and philosophers. And if they sound extreme, consider that only a century ago, the idea that space could stretch, that the universe had a beginning, that atoms were mostly empty space, were all considered outrageous. Progress doesn't just answer old questions, it opens up entirely new fields of inquiry that challenge our assumptions. So the question is not, should we care, but how could we not? Every discovery made in astrophysics, cosmology, or quantum theory is a mirror we hold up to ourselves. When we map the curvature of space-time, we are mapping the rules that govern not only stars and galaxies, but also the atoms in our bodies. When we investigate the nature of black holes, we are really investigating the boundaries of knowledge, where information goes, what survives death, what lies beyond what we can see. And when we peer into the void to find no evidence of extraterrestrial intelligence, we are forced to confront the silence with questions about loneliness, fragility, and what we are meant to become. Could it be that we are the first to reach this stage? Could we be the only sentient beings in a galaxy full of lifeless worlds? If so, what responsibility do we bear? What should we do with the knowledge that we might be the only voice the universe has ever produced that can ask why? These mysteries aren't abstract. They influence how we educate, how we invest in technology, how we structure our goals as a civilization. The potential discovery of life on Europa, or Mars, or a distant exoplanet would trigger a global redefinition of biology, ethics, religion, and law. It would upend centuries of belief systems and open entirely new ethical questions. How do we relate to non-human life? What rights does alien intelligence have? How do we communicate? Who speaks for Earth? Similarly, the ability to manipulate gravity, harness dark energy, or create stable wormholes would transform human society from a planetary civilization into an interstellar one. It would alter geopolitics, economics, identity. These are not distant science fiction dreams. They are the logical consequences of scientific progress. And they are unfolding in real time, right now, on the edges of what we know. So, what do you believe? Do you think we're alone? Or do you suspect that the silence is deceiving? Do you believe the universe is fundamentally knowable? Or do you think some truths lie forever beyond the reach of human reason? Do you think we should pour resources into space exploration? Or focus inward on Earth's immediate problems? Are these two goals mutually exclusive? Or could exploring the cosmos inspire solutions at home? These are questions that demand discussion, not just among experts, but among everyone. In classrooms and living rooms, in cafes and on social media, at dinner tables and in policy rooms. They are the questions that shape our identity as a species, because how we think about the cosmos reflects how we think about ourselves. This is an invitation to engage, not passively, not as a spectator, but actively as a thinker, a dreamer, a citizen of the universe. It doesn't matter if you don't know the math or can't explain string theory. What matters is that you care enough to wonder, to ask what's out there, to ask what that means for us. Maybe you've never thought about the implications of quantum entanglement, or the edge of the observable universe, or the idea that time may not be fundamental. But now that you have, what do you think? Should we accept the idea that we live in a simulation? Should we fund the search for extraterrestrial life? Should we build telescopes so powerful they can see the first moments after the Big Bang? Or is it all a distraction from problems here on Earth? Your opinion matters because this conversation belongs to humanity, not just to scientists. The universe is the ultimate equalizer. It doesn't care about your race, religion, wealth, or politics. It treats all matter and energy the same. But how we interact with it, how we explore, interpret, and dream is deeply human. And this interaction has the power to unite us. Imagine if the next generation grew up not just learning facts about planets, but feeling emotionally connected to the story of the cosmos. Imagine if people felt as much urgency and hope about solving cosmic mysteries as they do about elections or celebrity news. Imagine if discovering a new exoplanet generated as much excitement as winning a World Cup. Why shouldn't it? Isn't it just as meaningful, if not more, to uncover a world orbiting a distant star, one that might host life, might hold answers, might change everything? And what role will you play? Will you be the one to write the story, share the data, teach the child, ask the hard question? Will you support the missions, amplify the wonder, protect the science? Or will you let the mystery pass you by, content to live in the known, never reaching beyond the curtain? That choice is yours. But the universe isn't waiting. It's unfolding every moment, light traveling across billions of years just to reach your eyes. Gravitational waves rippling through space-time, distant worlds orbiting stars in quiet revolutions, whispering that something more is out there. You don't need to be an astronaut to explore. You don't need to be a physicist to understand. All you need is the willingness to engage, to be part of the conversation. Because every great leap in human history started with a question asked in the dark by someone who refused to accept the limits of the known. What will your question be? And when you ask it, who will you ask it with? Maybe you'll debate with friends about whether multiverses are real. Maybe you'll start a blog about gravitational lensing. Maybe you'll explain time dilation to your younger sibling. These may seem small, but they are seeds of curiosity, of engagement, of transformation. And from these seeds can grow a generation that is not only informed, but inspired. A generation that doesn't just inherit the stars, but reaches for them. So ask the question, share the thought, challenge the assumption, start the conversation, because the cosmos is not finished revealing itself. There are mysteries that have not yet been imagined, theories not yet written, realities not yet born. And the greatest mystery of all might not be what lies in the void but how we choose to respond to it. Will we be afraid, or will we be curious? Will we look away, or will we lean in? The universe is calling, not with answers, but with possibilities. And every time you wonder, every time you imagine, every time you care, you answer back.
Imagine standing on the edge of existence, suspended in the silence between stars, where time has no clear beginning and the future stretches into the infinite. All around you, the universe hums, not with noise, but with the silent tension of motion, of radiation, of gravity unfolding its ancient script. There are no walls here, no ceilings or floors, only endless black speckled with islands of light, galaxies drifting like slow, luminous snowflakes in a cosmic current that has no shore. Each galaxy is a sprawling metropolis of stars, dust, gas, and dark matter, rotating around invisible centers, forming clusters and filaments that extend across unimaginable distances. You are not simply a visitor in this setting, you are a fragment of it. The atoms in your body were forged in stars that lived and died before Earth even formed, and now here you are, conscious and aware, in the midst of a story that spans 13.8 billion years and counting. Let the atmosphere take hold. The night sky we see from Earth is only the faintest whisper of what lies beyond. To truly understand the cosmos, you must let go of ordinary scale. The Milky Way, our galaxy, stretches over 100,000 light-years across, containing more than 100 billion stars. And yet it is but one spiral in a supercluster of galaxies, a small thread in the vast cosmic web. These structures are not evenly distributed. They form intricate filaments and walls, with enormous empty voids in between, regions of space so vast and empty they contain almost nothing at all. These voids are the dark lungs of the universe, where no light pierces, no sound escapes, and gravity itself seems to rest. In contrast, the luminous tendrils of the cosmic web are bustling with galactic cities, bound together by the invisible scaffolding of dark matter. Though we cannot see dark matter directly, we know it is there, not through speculation, but through the subtle gravitational pull it exerts on galaxies and light. Without it, the universe would be chaotic and shapeless. With it we see order, structure, form. Zoom in closer and you'll find stars being born in glowing nebulae, vast clouds of gas and dust lit from within, swirling with the pastel hues of cosmic chemistry. These stellar nurseries, like the Orion Nebula or the Pillars of Creation, are more than beautiful. They are the cradles of new solar systems, where gravity pulls atoms together until nuclear fusion ignites and a new star begins to shine. Around these stars, planets form from the leftover debris, coalescing over millions of years, perhaps with their own oceans, mountains, and atmospheres. Somewhere out there may be even life, but space is not only a birthplace, it is also a graveyard. Massive stars burn hot and fast, collapsing into supernovae, explosions so powerful they can outshine entire galaxies for a brief time. What remains may be a neutron star, denser than imagination allows, spinning hundreds of times per second, or a black hole, an object so compact that not even light can escape its grasp. Black holes are not just cosmic monsters, they are key players in the cosmic story. At the heart of most galaxies, including our own, lies a supermassive black hole, millions or even billions of times the mass of our sun. These entities warp space-time to extremes, bending light, slowing time, and possibly connecting us to other realms entirely. Around them swirl accretion disks of hot gas, forming luminous quasars that can be seen across billions of light-years. These are not just objects of destruction, they are engines of creation, regulating star formation, sculpting galaxies, and perhaps encoding the boundaries of what we can ever know. The event horizon, the point of no return, is not a wall but a mystery, an interface between the known universe and something we can only theorize about. What lies inside? A singularity, a passage to another dimension, a mirror universe? These questions draw us deeper, not only into physics, but into philosophy. Above and beyond individual phenomena, the whole structure of the universe pulses with mystery. We speak of dark energy, an unknown force accelerating the expansion of space itself, stretching the fabric of reality like a rubber sheet pulled at every edge. Its nature is one of the greatest enigmas in science. Unlike matter, dark energy doesn't clump or attract, it repels. It pushes galaxies apart, faster and faster, defying gravity and undermining our predictions of a slow cosmic cooling. Some theories suggest it may cause the universe to expand forever, ending in a cold, dark fade-out known as the heat death. Others imagine a violent rebirth, the Big Rip, where the acceleration tears galaxies, stars, and eventually atoms apart. We don't yet know, but the mere fact that we can ask, measure, and speculate is a testament to the power of scientific curiosity. To build such knowledge, countless individuals have dedicated their lives to peering into the void. Their names form a constellation of minds that shaped our view of the cosmos. Edwin Hubble, who proved the universe is expanding. Georges Lemaitre, who first envisioned the Big Bang. Albert Einstein, whose equations reshaped time, space, and gravity. Vera Rubin, who uncovered evidence for dark matter in galactic rotation. Stephen Hawking, who brought black hole thermodynamics into the public consciousness. Carl Sagan, who reminded us that we are star-stuffed contemplating the stars, and today others carry the torch. Kip Thorne, theorizing about gravitational waves and time warps. Katie Bouman, helping produce the first image of a black hole. Avi Loeb, exploring the possibility of interstellar visitors. Their work is more than science. It is a language of awe, a discipline of asking what lies beyond the boundaries of perception. Modern instruments give these minds tools of unprecedented power. The Hubble Space Telescope gave us a window to the past, revealing galaxies as they were billions of years ago. The James Webb Space Telescope now takes us even further, peering into the era of first light, when the universe was only a few 100 million years old. These instruments do not merely take pictures, they gather spectra, detect invisible wavelengths, reveal the composition of exoplanet atmospheres, and help decode the hidden patterns of cosmic evolution. Alongside them, Earth-based observatories like ALMA, the Very Large Telescope, and LIGO detect radio waves, gravitational waves, and other subtle signals. Each whisper from space adds a word to the poem of the cosmos, each discovery a brushstroke on the canvas of universal truth. The atmosphere we breathe here, this narrative of space, isn't just built from facts, it is built from wonder. Scientific curiosity is not cold or detached, it is a fire, burning with the same intensity as the stars it seeks to understand. To walk through the halls of cosmology is to walk through a temple of questions, each one more humbling than the last. What came before the Big Bang? Are there dimensions curled up too small to see? Can time run backward? What is the fate of information swallowed by a black hole? These are not idle puzzles. They define the frontier between what is known and what could yet be known. And through it all, we are reminded that we are part of this universe. Not separate, not observers from the outside, but active participants. Every time you think about space, you are engaging in a form of communion with the cosmos. The awe you feel is not an accident. It is a natural response to the recognition of scale, of beauty, of mystery. When you gaze at a photo of a distant galaxy, remember that the light took millions of years to reach you, that you are seeing something as it was long before humans walked the earth. That photon passed through unimaginable distances, untouched by time, only to be absorbed by your eye in a single fleeting moment. That connection between something so vast and something so personal is the essence of the cosmic experience. The tone of this setting is not one of cold analysis. It is a cathedral of silence and motion, a realm where science becomes poetry, and equations trace the outlines of eternity. The language of the universe is not only written in math and physics, but in wonder, curiosity, and humility. To enter into it is to accept that some questions may never be answered, and yet we ask them anyway, not because we expect answers, but because the asking itself transforms us. It makes us explorers, artists, seekers of truth in a sea of darkness. This atmosphere, this immersive, reverent awareness of the cosmos, is what science strives to preserve, not as a relic of old myths, but as a living practice of inquiry. We are not done discovering, not even close. The universe is still unfolding its secrets, in quantum fields, in gravitational echoes, in signals from distant planets. Somewhere out there, perhaps even now, is a world orbiting a sun like ours, with oceans and skies, with life gazing up at its own stars, wondering if it is alone. Perhaps one day, our signals will reach them, or theirs will reach us. And when that day comes, we will not greet them as strangers, but as fellow passengers in the same cosmic story. To build an atmosphere of the cosmos is to invite people not just to learn, but to feel, to awaken not just knowledge, but wonder. This is the heart of the scientific journey. It begins in silence, expands through observation, and blossoms into revelation. And every person who hears the call, who chooses to look up and ask, becomes part of that story, not a spectator, but a participant, not a footnote, but a verse. The cosmos is not only above us, it is within us, and in the space between stars, between thoughts, between questions and answers, we find the place where imagination meets reality, and where the infinite begins. The search for the edge of the universe is not just a physical journey, it is a philosophical one that leads us not to clear answers, but into a maze of paradoxes, constraints and humbling realizations. From the moment humanity first looked skyward and tried to understand what lies beyond the stars, we have faced the boundaries of perception and reason. We've built telescopes that can peer back in time, capturing the faint glow of galaxies that existed billions of years ago, and we've launched space probes beyond the reach of sunlight. Yet for all our progress, a haunting truth whispers beneath every new discovery: we may never truly find the end, not because it doesn't exist, but because the very structure of reality may not allow us to see it, or worse, because the concept of an edge may be fundamentally flawed. This is the quiet conflict at the heart of cosmology. We seek something that our tools, our minds, and perhaps even the universe itself may forever prevent us from grasping. And the signs of this conflict are already here, scattered like cosmic breadcrumbs across the last century of scientific exploration. One of the earliest hints that the universe might not be what it seems came from Einstein's theory of general relativity. While the mathematics allowed for dynamic expanding solutions, Einstein initially added a cosmological constant to force the equations into a static universe, because that was what the prevailing worldview demanded. But the universe, as Edwin Hubble would later confirm, was not static, it was expanding. This expansion suggested a beginning, a Big Bang, but it also implied something more disturbing, that the further away we look, the younger and more compressed the universe becomes. There is no central point, no edge like the lip of a bowl, because space itself is stretching. Every galaxy is moving away from every other galaxy, not through space, but with space. The implications of this expansion ripple outward, forcing us to confront the reality that the observable universe, what we can see, is not the same as the full universe. In fact, the more space expands, the more galaxies move beyond our cosmological horizon. They do not disappear, but their light will never reach us. We are witnessing a slow vanishing, a universe that grows not only in scale, but in isolation. The very nature of light and time means we cannot see everything that exists. The observable universe is limited by the age of the cosmos and the speed of light. We can see about 46.5 billion light-years in any direction, even though the universe is only 13.8 billion years old, because space itself has expanded during the time it took the light to travel. But beyond that, there may be more, possibly infinitely more, that we will never see, no matter how powerful our instruments become. This isn't a temporary limitation, it's a hard wall written into the structure of space-time, and yet we press against it. Not because we think we'll break through, but because we must understand how close we can get. The desire to know the edge, to chart the full map, is as human as the impulse to breathe. But what if the map has no edge? What if space is curved in on itself, like the surface of a sphere, infinite in extent, but without boundaries? Or worse, what if space is flat and infinite, but only one part of a much larger multiverse, with domains so different from ours, that we could never communicate, never compare, never even be sure they exist, except through fragile theoretical inference? These questions are not just speculative, they arise directly from the math, from observations, and from the contradictions we find at the intersection of the very large and the very small. General relativity works beautifully to describe gravity and large-scale structure, but it breaks down at singularities, places like the center of a black hole, or the moment of the Big Bang. Quantum mechanics, meanwhile, gives us incredible predictive power at the subatomic scale, but seems incompatible with gravity. For decades, physicists have tried to reconcile the two in a theory of quantum gravity. String theory, loop quantum gravity, and other frameworks have attempted to unite the forces, but none have yet delivered a complete testable model. The tension between these theories is not just academic, it is a sign that we are missing something profound, somewhere, Hidden in the equations, or in the assumptions that guide them, is a contradiction waiting to be resolved, or maybe not resolved, maybe just understood as a paradox that must be lived with. One of the most profound examples of this paradox is the holographic principle. Based on insights from black hole thermodynamics and quantum information theory, it suggests that all the information in a volume of space can be encoded on its boundary, like a hologram. If this is true, then our three-dimensional reality may be an emergent phenomenon, a projection of a more fundamental, two-dimensional physics. This would mean that our sense of depth, of movement, of extension, is not as real as we think. It's not illusion in the sense of fantasy, but it might be illusion in the sense of derived experience. This idea forces us to question not just what the universe is, but what it means to observe and interact with it. How can we find the edge of something that may not even be a volume in the way we assume? The deeper we look into space, the more we are also looking back in time, but this too has limits. The cosmic microwave background, the afterglow of the Big Bang, is as far as light-based observation can go. It is the surface of last scattering, beyond which the universe was opaque. To see further, we would need to detect neutrinos, or gravitational waves, from earlier epochs. We are trying, building new detectors, refining techniques, but even these may only get us so far. The first Planck time after the Big Bang, a fraction of a second so small, it's almost meaningless in ordinary language, remains hidden. To access it would require energies and resolutions we may never achieve. There may be a fundamental limit to what can be known, not because we lack ingenuity, but because the universe has an epistemological horizon. Knowledge itself may have an edge. Observational constraints are not just physical, they are technological, practical, and economic. To map the entire sky, at the resolution we desire, requires instruments in space, away from Earth's atmosphere. To study dark energy, or dark matter, requires detectors, shielded from cosmic radiation. To test theories about extra dimensions, or string vibrations, requires particle accelerators, far beyond our current capabilities. These are not small hurdles, they are mountains, and we must ask ourselves, as individuals, and as a species, how much we are willing to invest in climbing them. Because the road ahead does not lead to quick answers, it leads to deeper, more precise forms of uncertainty. Every new discovery adds detail to the map, but also opens new territories of ignorance. The edge keeps moving. The more we know, the more we realize we don't know. Scientific understanding is not a straight line, it is a spiral, or perhaps a web, circling around deeper truths, revisiting old assumptions with new data, refining models, discarding once sacred principles. In the 19th century, people believed the universe operated on clockwork Newtonian laws. In the 20th century, we discovered relativity and quantum mechanics, and our concept of reality was shattered and rebuilt. In the 21st century, we face dark energy, dark matter, the multiverse, the holographic universe. What will come next? What current beliefs will seem quaint or naive to the future? Perhaps we are like flatlanders, two-dimensional beings, trying to understand a three-dimensional world. Perhaps our very language and cognition are ill-equipped to grasp the true nature of reality. This is not a cause for despair. It is the most powerful story we have. The fact that we are capable of asking, of reaching, of confronting our limits, that is what defines us. The conflict we face in cosmology is not failure, it is a reflection of our growth. We are no longer satisfied with simple stories. We demand coherence. We test hypotheses. We accept uncertainty. But this acceptance comes with a cost. It means acknowledging that some questions may remain unanswered. It means letting go of finality, of closure, of the fantasy that the universe will one day be fully explained. It means living in a story, without a final chapter, at least not one we can read. And so we return to the edge, not as a place, but as a metaphor. The edge is not out there in space, it is within us. It is the edge of knowledge, of perception, of imagination. It is the place where our desire to understand meets the vastness of what remains unknown. It is a horizon that recedes as we approach, not because it is running away, but because we are growing. The conflict we face is between the infinite and the finite, between the endless complexity of the universe and the limited capacity of the human mind. But even this limitation is a source of beauty, because within it lies the essence of the scientific spirit, not the belief that we can know everything, but the courage to keep asking, even when the answers seem forever out of reach. We may never find the true edge of the universe. We may never see beyond the cosmic horizon. We may never resolve all paradoxes, or build a perfect theory of everything, but in the pursuit, in the conflict itself, we find meaning. The struggle to understand is what makes us who we are, and so we continue, staring into the darkness, listening for echoes, mapping the silence, not because we expect a final answer, but because the journey itself is the most human act of all. At the heart of modern cosmology lies a fundamental conflict, one that is not simply a clash between rival theories, but a reflection of our deepest philosophical and scientific uncertainties. The universe, vast, mysterious, and elegant, has revealed much over the past century, yet the more we uncover, the more the foundations beneath our understanding begin to tremble. We live in an age of precision measurement and observational triumphs, where space telescopes can see galaxies billions of light years away, gravitational wave detectors can hear the ripples of merging black holes, and satellites can map the cosmic microwave background with exquisite detail. And yet, despite this torrent of data, some of the most basic questions about the universe remain not only unanswered, but fiercely contested. What is the shape of the cosmos? Is it finite or infinite? Does it have an edge? Or is the idea of an edge itself a human illusion? These are not trivial academic questions. They strike at the core of how we define space, time, and existence, and they pit the sharp tools of observation against the wild, sometimes paradoxical terrain of theoretical physics. One of the most persistent tensions in cosmology is the division between what we can observe and what we can imagine. The observable universe, roughly 93 billion light-years in diameter, is the portion of space from which light has had time to reach us since the Big Bang. But beyond this limit, space may go on endlessly, or not at all. General relativity allows for both scenarios, depending on the curvature and overall geometry of the universe. In a positively curved universe, space would be finite, but unbounded, like the surface of a sphere. In a flat or negatively curved universe, space could be infinite, extending forever in all directions. Current measurements of the cosmic microwave background and the large-scale structure suggest that the universe is flat to a high degree of precision, which implies it might be infinite. But this interpretation is far from certain. An infinite universe cannot be directly observed or confirmed. We can only extrapolate from what we see, and every extrapolation is based on assumptions that could collapse under the weight of new data or more refined theory. Complicating matters further is the possibility that what we perceive as flatness could be a local fact, like standing on Earth and thinking it's flat because we cannot see the curvature. If the universe is slightly curved on a larger scale than we can observe, our measurements might be misleading. Moreover, inflationary theory, which posits that the universe underwent a rapid exponential expansion in the first fraction of a second, predicts that any initial curvature would have been smoothed out, leaving space very close to flat, regardless of its true topology. But inflation itself is a theory still awaiting direct confirmation. It solves many problems, such as why the universe is so homogeneous and why the cosmic microwave background is so uniform. But it also introduces new puzzles. What caused inflation to start, and why did it stop? Does it continue in other regions, leading to eternal inflation and the birth of other bubble universes? If so, our observable universe could be just one pocket in a vast multiverse, each with its own physical laws and constants. This is a breathtaking possibility, but one that may be forever beyond the reach of observation, and therefore fundamentally untestable by traditional scientific methods. These are the kinds of conflicts that divide cosmologists today. On one side are those who argue that a theory, no matter how elegant, must make predictions that can be tested, falsified, and refined through empirical data. On the other side are theorists who believe that the scope of reality may extend beyond our capacity to test it, and that the role of theory is to chart these unobservable realms with logical coherence, even if experimental proof remains elusive. String theory and the multiverse hypothesis are prime examples. String theory aims to unify all known forces under a single framework by modeling particles as vibrating strings in higher dimensional space. It offers a rich mathematical landscape, but has so far failed to produce experimentally verifiable predictions. Critics argue that without observational support, such theories drift into metaphysics. Supporters counter that the lack of current evidence does not invalidate the theory's promise, and that future technology may yet provide the necessary tools. The debate over the finiteness or infiniteness of the universe mirrors these philosophical divisions. An infinite universe challenges our intuition. It implies not just an endless stretch of stars and galaxies, but also infinite repetitions, an endless number of Earths, of histories, of versions of ourselves. It breaks down probability and makes every outcome inevitable somewhere. It's a vision that is simultaneously majestic and unsettling, hinting that meaning and uniqueness may dissolve in an ocean of endless variation. A finite universe, on the other hand, offers a comforting boundary, a sense of wholeness and containment, but it too comes with complications. What lies beyond the edge, if there is one? Is it an actual boundary, or a conceptual one? Could space wrap around on itself,
like a higher dimensional analog of a three-dimensional torus, so that traveling far enough in one direction would eventually bring you back to your starting point. These topological possibilities are allowed by general relativity, but again, they are difficult, perhaps impossible to test conclusively. Then there is the issue of cosmic acceleration, driven by dark energy. The discovery that the universe's expansion is speeding up, rather than slowing down, shocked scientists in 1998. It suggested the existence of a repulsive force embedded in the fabric of space itself, a kind of anti-gravity that drives galaxies apart at ever-increasing speeds. This acceleration means that more and more of the universe is slipping beyond our observational reach. Eventually, only the local group of galaxies will remain visible. This isn't just a future scenario, it is already happening. Every second, more galaxies pass beyond the cosmic horizon, their light redshifted into oblivion. This creates a growing tension between theory and observation. How can we construct a complete model of the universe when the universe itself is disappearing from view? Even the structure of time is in question. According to some quantum gravity models, time may not be fundamental. It may emerge from deeper, more abstract properties of space or information. If time is not fundamental, then our concept of causality, the sequence of events, the arrow of time from past to future, must be re-examined. This has implications not just for physics, but for how we understand existence itself. What does it mean to speak of a beginning of time, if time is emergent? Could the Big Bang be a bounce, a phase transition from a previous universe, or a fluctuation from a timeless quantum field? Again, these are not questions we can easily test, and yet they sit at the heart of our attempt to define the edge, not just spatially, but temporally. Another layer of conflict arises when quantum mechanics enters the picture. The tension between quantum mechanics and general relativity is perhaps the most famous unresolved problem in physics. Each theory works flawlessly within its domain, yet they are incompatible at fundamental levels. Black holes, where extreme gravity and quantum effects collide, expose this conflict in dramatic ways. Do they destroy information, as classical physics implies, or preserve it, as quantum mechanics demands? Stephen Hawking's famous proposal that black holes radiate and evaporate led to the so-called information paradox, which remains unresolved, despite decades of debate. The resolution of this paradox could either confirm the primacy of quantum theory, or force a rewriting of our most cherished assumptions. Either outcome would redefine our understanding of boundaries, causality, and the ultimate fate of the universe. And yet, in the midst of all these tensions, the scientific enterprise continues, not paralyzed by uncertainty, but animated by it. The struggle to define the edge of the universe is not just a scientific conflict, it is a deeply human one. It reveals our desire to grasp the totality of existence, to impose structure on the infinite, to find closure in a cosmos that may offer none. It also highlights the limits of human cognition. We evolved to throw spears and read facial expressions, not to understand 10-dimensional space or infinite expansion. Our brains are finite, our tools limited, our language imprecise. Yet here we are, attempting to model the entire universe, with equations on chalkboards and data from faint points of light. In this conflict, there are no easy answers. Every gain in knowledge exposes a new horizon of ignorance. Every elegant theory opens a path to contradictions. Every new observation confirms some models and refutes others, but never seems to close the case. We are in a constant state of revision, refinement, and re-evaluation. This is not a weakness of science, it is its strength. Unlike dogma, science welcomes conflict, it thrives on it. It turns paradoxes into engines of progress, but that progress is neither linear nor comfortable. It demands humility, patience, and the willingness to live without certainty. Ultimately, the conflict over the edge of the universe is a mirror. It reflects not only the cosmos, but ourselves, our need for meaning, our discomfort with ambiguity, our hope for clarity, and our fear of the unknown. Whether the universe is finite or infinite, whether it has an edge or is boundless, whether time is fundamental or emergent, these questions challenge us to expand the boundaries of thought. They force us to grow beyond the constraints of intuition, to embrace complexity.
If the universe has no edge, no boundary to its shape, no endpoint to its expanse, no final wall we can reach and touch, then we are living within a reality that challenges not only our scientific assumptions, but our deepest philosophical convictions. The concept of an edge, after all, is rooted in the way humans experience the world. We build fences, climb mountains, sail to shorelines, cross borders. We've evolved to see space as limited and measurable, a framework that can be navigated and understood. But the cosmos, it seems, does not conform to that logic. It mocks our sense of finality and forces us to reconsider not just where we are, but what it means to be anywhere at all. If there is no edge to the universe, then we are not at the center, nor are we drifting toward a boundary. We are simply immersed in a continuum that stretches without end, and the implications of that realization ripple through every corner of human thought, from physics to metaphysics, from existential meaning to mathematical abstraction. In physics, the absence of an edge forces a reevaluation of the models we've built to describe the cosmos. General relativity, our most trusted theory of gravity and space-time, offers solutions for both finite and infinite universes, depending on the curvature of space. If space is closed, like the surface of a sphere, it is finite but unbounded. Travel far enough in one direction, and you could in theory return to your starting point without ever encountering an edge. But if the universe is flat or open, as current measurements of the cosmic microwave background suggest, it may be infinite, extending forever without repetition, without loops, without limits. This has profound consequences for cosmology. An infinite universe implies infinite matter, infinite configurations, and perhaps even infinite versions of ourselves, playing out every possible variation of events. It means that the Big Bang was not an explosion into space, but the beginning of space itself, an event that occurred everywhere at once, with no center and no perimeter. Such a model stretches our understanding of time as well. If space has no edge, then time may also be unbounded. But this leads to contradictions in our attempts to reconcile quantum mechanics with gravity. Quantum field theory, which governs the behavior of particles and forces, assumes a flat, infinite space as a backdrop. But gravity, as described by general relativity, bends and warps that space in ways that defy the assumptions of quantum theory. This inconsistency is not just academic, it means that our most successful theories do not agree on what the universe even is. The lack of an edge removes a potential boundary condition that could help us unify these models. Without a way to define where the universe ends, we lose one of the tools that might allow us to test competing theories, especially those involving the shape, topology, and ultimate fate of the cosmos. Moreover, if the universe has no edge, then its fate becomes even harder to predict. A finite universe could one day collapse in a big crunch, or undergo a big bounce, cycling through expansions and contractions. But an infinite universe may expand forever, growing colder and emptier as galaxies drift apart beyond the reach of light, ending in a heat death, a scenario in which entropy reaches a maximum and all processes cease. Alternatively, the acceleration of cosmic expansion caused by dark energy could lead to a big rip, in which space itself is torn apart, disassembling galaxies, stars, planets, and finally atoms. These outcomes are not merely speculative. They are grounded in real equations and data, yet the lack of boundaries means we may never know which, if any of them, is correct. The infinite resists certainty. It offers no frame of reference, no closure, no safe harbor of finality. The philosophical implications are even more staggering. Human beings have always sought to define themselves in terms of boundaries between life and death, self and other, order and chaos. The edge is where we place our gods, our fears and our hopes. It's where myths are born. The edge is the unknown, the place beyond the map where dragons dwell. But if there is no edge, then what becomes of those myths? What becomes of our place in the universe? The realization that the cosmos has no boundary challenges the anthropocentric view of the universe as a stage for human experience. We are not special because we are at the center. We are not at the center at all. We are not near the beginning or the end, because in a universe without edges there are no privileged points. Every location is as ordinary or extraordinary as any other. This undermines some of our oldest metaphysical assumptions. If there is no edge, then there is no outside. The universe is not expanding into something, it is all there is. Space itself is not a container, but a dynamic fabric, a field of relationships between energy and geometry. The idea of outside the universe becomes meaningless, a linguistic artifact left over from an era when the sky was a dome and Earth was the center, and if there is no outside, then where could a creator reside? The absence of an edge has implications for theology as well, especially for cosmologies that depend on a creation event occurring from outside of space and time. It doesn't disprove such ideas, but it does force them to evolve, to become more abstract, more aligned with the mysterious laws of quantum uncertainty and higher dimensional topology than with classical narratives of beginning and end. For individual human beings, the emotional impact of an infinite, edgeless universe can be both liberating and terrifying. On one hand, it frees us from the claustrophobia of finitude. There is always more to explore, more to know, more to imagine. We are not trapped in a cosmic box. We are part of an unfolding tapestry without limit, a network of connections and possibilities that extend forever. On the other hand, the sheer scale of infinity can provoke existential vertigo. If there is no edge, no end, then what does it mean to make choices? Does anything matter in the face of endless repetition and limitless space? These are the questions that haunt the philosopher as much as the physicist. They challenge us to find meaning not in the totality of the universe, but in the local, the immediate, the relational. Meaning becomes something we create, not something the cosmos gives us. Yet these philosophical and emotional responses should not be mistaken for scientific conclusions. The lack of an edge is not a belief or a preference, it is the implication of the best data we currently have, and that data pushes us to develop new physics. The standard model of particle physics, combined with general relativity, has been remarkably successful, but it cannot explain dark matter, dark energy, or the origin of the universe. It cannot unify gravity with the other fundamental forces. It cannot answer whether space is discrete or continuous, finite or infinite. To go further, we need new theories, models that incorporate quantum gravity, that explain the vacuum energy driving cosmic acceleration, that reveal the structure of space-time at the Planck scale. We need tools that can describe the universe not just as it appears, but as it truly is, even when that reality resists visualization. This need for new physics is urgent. The more we learn, the more we realize how incomplete our models are. The edgeless universe is not a final answer, it is a symptom of deeper ignorance. We have glimpsed the outline of a reality that goes beyond 3 dimensions, beyond classical causality, beyond linear time. We suspect that space and time may be emergent properties of a deeper quantum substrate, that information may be more fundamental than matter, that geometry and entropy are more closely linked than we ever imagined. These are not ideas born of whim or fantasy. They arise from the paradoxes and conflicts within our current theories. They are the natural next steps in a journey that began when we first looked up and wondered what lay beyond the stars. And in that journey, the absence of an edge is not a wall but a challenge. It asks us to think bigger, to feel deeper, to accept that the universe is not designed to be easily understood. It resists finality. It offers no clear endpoint. But in doing so, it offers something more profound, a continuous horizon of discovery, an endless invitation to question, to explore, to dream. We may never find the edge of the universe because there may be no edge to find, but that does not mean the search is meaningless. On the contrary, the very act of searching brings us closer to truth, not because we reach it, but because we become more capable of understanding what truth might be. If the universe has no edge, then perhaps the only edge that matters is the one we carry within us, the edge of thought, of imagination, of knowledge. It is that edge we must continue to expand, not with the hope of mastering the cosmos, but with the humility of knowing we are part of it. We are not outsiders looking in, nor central figures in a cosmic play. We are participants in a vast, open-ended process of becoming. And that process, that dance of mystery and meaning, is the greatest story ever told, one with no beginning, no end, and no edge. There are moments in the history of science that forever change our understanding of the universe, turning points where long-held assumptions fall away, and a new vision of reality emerges from the ashes of the old. For cosmology, the study of the universe's structure, origin, and evolution, the past few decades have delivered not just one such moment, but a cascade of them. These revelations have not only reshaped our conception of space and time, but have forced us to confront a more bizarre, dynamic, and elusive cosmos than anyone had imagined. In the process, they've drawn sharp lines between what we thought we knew and what the universe is now revealing to us. This is the story of that turning point, a story written in wavelengths invisible to the naked eye, in the silent dance of galaxies, in the slight warps of light through dark matter, and in the mysterious pressure known as dark energy that now defines the future of everything. For most of the 20th century, cosmology progressed under the assumption that gravity was the dominant force shaping the universe. Albert Einstein's theory of general relativity had provided an elegant and predictive framework to understand how mass bends space-time and how that curvature dictates motion. Edwin Hubble's 1929 discovery that the universe was expanding gave us the concept of the Big Bang, a single moment of explosive birth that launched the cosmos into motion. For decades, cosmologists argued over the ultimate fate of the universe. Would it expand forever, slow down and reach a stable size, or collapse back into a big crunch? All outcomes were thought to depend on the amount of matter in the universe, both visible and invisible. But in 1998, the universe surprised us. In an attempt to measure the rate of cosmic deceleration, 2 independent teams studying distant Type Ia supernovae discovered something shocking. Instead of slowing down, the expansion of the universe was accelerating. This finding, seemingly minor at first, was in truth a seismic shift in physics. It meant that some unknown force, now called dark energy, was acting like a kind of anti-gravity, pushing galaxies apart at an ever-increasing rate. This force, which no one had predicted or understood, seemed to make up about 70% of the total energy content of the universe. Dark energy didn't just change the answer to how the universe would end, it changed the question entirely. It meant that the structure of the cosmos wasn't governed solely by matter and gravity, but by a repulsive energy built into the very fabric of space-time. Dark energy became the dominant player in the cosmic story, yet its nature remains one of the greatest mysteries in science. Is it a cosmological constant, as Einstein once proposed and then discarded? Is it a new field like the Higgs field? Is it a dynamic force that will change over time? Or is it the first glimpse of a deeper, undiscovered theory of space-time itself? To even begin answering these questions, scientists needed better tools, more precise instruments that could see further, deeper, and with greater clarity than ever before. And in response, humanity entered a golden age of astronomical technology. The Hubble Space Telescope, launched in 1990, became our window into the deep past. Orbiting above the distortion of Earth's atmosphere, Hubble gave us crystal-clear images of distant galaxies, gravitational lensing, and star-forming regions. It measured the expansion rate of the universe with unprecedented accuracy, and through its deep-field images, revealed thousands of galaxies in what once looked like empty patches of sky. But as powerful as Hubble was, it also revealed the limitations of our vision. To understand the universe in its infancy, just a few 100 million years after the Big Bang, astronomers needed to see in infrared wavelengths, beyond what Hubble could detect. Thus began the race to build something even more powerful. The James Webb Space Telescope. Launched in late 2021 after decades of development, the JWST marked another turning point. With its enormous segmented mirror and sensitive infrared detectors, it peered deeper into time than any telescope before. It began capturing images of ancient galaxies that formed earlier than models had predicted, challenging our assumptions about how quickly structure formed in the universe. Some of these galaxies appeared too massive and well-organized for their age, suggesting either that our understanding of galaxy formation was incomplete or that some unknown process had accelerated their evolution. Webb also began studying the atmospheres of exoplanets, detecting water vapor, methane, and carbon dioxide, opening the door to the eventual discovery of life beyond Earth. These findings, while only the beginning of Webb's mission, already suggested that the universe is not only more ancient than we imagined, but more efficient at creating complexity than we realized. Beyond telescopes, the rise of gravitational wave astronomy provided yet another axis of revelation. With the detection of gravitational waves in 2015 by LIGO, a century after Einstein predicted them, we gained a new way to observe the universe through ripples in space-time itself. These waves, generated by collisions of black holes or neutron stars, carry information about regions of space we could never observe with light. Each detection confirmed the existence of extreme objects and offered clues about how common they are, how they evolve, and how they shape the universe. Gravitational wave astronomy also confirmed that black holes are not rare anomalies, but key components of galactic evolution. Their collisions and the resulting energy bursts shape the structure of galaxies, regulate star formation, and may even play a role in the cosmic balance of matter. Meanwhile, instruments like the Planck satellite refined our picture of the cosmic microwave background, the faint afterglow of the Big Bang, measuring tiny fluctuations in temperature and density that seeded the formation of galaxies. These fluctuations, imprinted just 380,000 years after the Big Bang, became the blueprint for everything that followed. From this data, we derived precise values for the universe's age, composition, and geometry. We learned that the universe is flat to within a 0.4% margin of error. That dark matter makes up 26%, dark energy 69%, and ordinary matter, the atoms that make up stars, planets, and people, only 5%. These numbers reoriented our perspective entirely. We are not the main ingredients of the cosmos, we are the seasoning. Yet we are also the only known entities capable of observing, questioning, and trying to understand it all. One of the most important consequences of these revelations is the growing realization that our current models, though powerful, are incomplete. The standard model of particle physics, while remarkably successful in describing known particles and forces, cannot account for dark matter or dark energy. It does not include gravity, and it does not offer a mechanism for the inflationary expansion that theory predicts occurred just after the Big Bang. Similarly, general relativity, though a beautiful and accurate description of gravity, breaks down at singularities and fails to mesh with quantum mechanics. These gaps signal the need for new physics,
Possibly a theory of quantum gravity that can unite the small with the large, the energetic with the curved. Candidates like string theory, loop quantum gravity, and emergent spacetime models are all being developed, each promising to answer old questions and raise new ones. But none has yet achieved the empirical validation that would elevate it to a new standard. And so we are in the midst of a great turning point. Not a single aha moment, but a sustained and accelerating revolution in thought. The implications stretch far beyond astronomy. If dark energy is a cosmological constant, it suggests a static backdrop to all cosmic events. If it is a field that changes over time, it may decay or increase, leading to future phase transitions, possibly ripping the universe apart or birthing a new one. If the expansion of the universe continues indefinitely, the observable universe will shrink, and future civilizations may lose access to the evidence of the Big Bang, left only with a dark sky and no memory of cosmic origin. If our theories are correct, we are living in the golden age of observational cosmology, the brief window when the universe is still young enough, bright enough and coherent enough for us to measure and understand. This moment matters. It is a moment of confrontation, not with enemies or obstacles, but with ignorance. We are looking out into the cosmos and realizing that the universe is not a fixed, comprehensible object, but a living process, filled with surprises, contradictions and mysteries. We have seen galaxies that shouldn't exist, dark forces we cannot explain, and mathematical boundaries we cannot cross. And yet the tools at our disposal, telescopes, detectors, accelerators, simulations, are growing in power, pushing those boundaries back a little further each day. The turning point we are experiencing is not just technological or theoretical. It is conceptual. It challenges the very way we define knowledge, truth, and understanding. It invites us to consider that reality may be layered, emergent, or even entangled with our act of observing it. It suggests that the universe is not simply a place, but a process, that being is not static but dynamic, woven through time and probability. And it tells us, with increasing clarity, that we do not yet know the full story, but we are beginning to see its outline. In that outline, we see that the universe is not just expanding in space, but in complexity. We are not nearing the end of knowledge, we are standing at the frontier of an intellectual expansion that may be as profound as the physical one it seeks to understand. We are discovering new kinds of energy, new forms of matter, new windows of observation. We are watching the universe evolve, and realizing that our understanding must evolve with it. We are being asked by the cosmos itself to grow. And perhaps the most remarkable part of all this is that it's happening now in your lifetime. You are living at a moment when the universe is giving up some of its deepest secrets. You are witnessing a shift, not just in facts but in worldview. The sky has always been a source of wonder, but now it is also a source of transformation. The night is no longer a canvas of static stars. It is a field of motion, structure, and mystery. And with every new image, every new dataset, every new theory tested and refined, we are rewriting what it means to exist. This is the turning point. Not the end of science, but the beginning of a new chapter, one where we no longer seek a single final answer but embrace a universe that is richer, stranger, and more dynamic than we ever dared to dream. The stars have not changed, but we have. And so has the story we tell about them. What if the questions we're asking about the universe are rooted in assumptions so fundamental and so flawed that they are leading us in the wrong direction entirely? What if the concept of space itself, of dimension and distance and continuity, is not what it appears to be? These are not idle philosophical musings. They are the heart of a growing shift in scientific perspective, a re-evaluation of the deepest structures that underpin reality. For much of modern cosmology, we've built our models around the idea that the universe is a three-dimensional arena through which matter moves and time flows, governed by classical geometry and relativistic curvature. But increasingly, scientists are discovering that this perspective may be limited, that space, time, and even gravity could be emergent properties, illusions that arise from more fundamental quantum rules operating at scales, and in ways we are only beginning to comprehend. At the forefront of this shift is the holographic principle, a radical theory suggesting that everything we perceive as three-dimensional may in fact be encoded on a distant two-dimensional boundary, a cosmic hologram in which depth is a projection, and the real universe is fundamentally informational. The holographic principle was born from the paradoxes surrounding black holes, and particularly the conflict between general relativity and quantum mechanics. In classical physics, a black hole is a region of space-time from which nothing, not even light, can escape. Its defining boundary, the event horizon, marks the point of no return. According to general relativity, any information that crosses the event horizon is lost forever. But quantum mechanics forbids information loss. The two theories were at war. Then in the 1970s, physicists Jacob Bekenstein and later Stephen Hawking proposed that black holes must have entropy, and that their entropy was proportional not to their volume, but to the surface area of their event horizon. This was unexpected. In thermodynamics, entropy typically scales with volume. The more stuff you have, the more microscopic configurations it can be in. But black holes didn't behave that way. Instead, their entropy suggested that the maximum amount of information that could be stored in a region of space depended not on its volume, but on its surface. This led to a stunning implication: perhaps the information about everything that happens inside a volume of space is actually encoded on its boundary. In other words, our perception of three-dimensional reality might be like a hologram, a projection from a deeper, flatter reality. This idea gained traction in the 1990s with the development of the ADS-CIS-CFT correspondence, proposed by Juan Maldacena. In this framework, a theory of gravity in a five-dimensional space, anti-de Sitter space, could be mathematically equivalent to a quantum field theory with no gravity on its four-dimensional boundary. The two descriptions were completely different in form. One involved curved space-time and gravity, the other involved flat space and quantum fields, but they described the same physics. This duality suggested that gravity itself might be emergent, not fundamental. And if gravity is emergent, then so might be space-time. The implications are staggering. It means that the universe as we perceive it may not be the most fundamental layer of reality. It means that what we call space may be nothing more than a construct derived from quantum entanglement and information processing. It suggests that the true description of the universe lies not in geometry, but in computation, logic, and probability. Changing our perspective in this way has cascading effects across all of physics and cosmology. If the universe is fundamentally holographic, then many of our traditional intuitions about locality, about causality, about dimensionality, must be re-examined. Quantum entanglement, for instance, which Einstein derided as spooky action at a distance, may be the glue that holds space-time together. In this view, entangled particles are not just connected across space, they may define space itself. The more entangled two regions are, the closer they are in an emergent geometric sense. As entanglement changes, so does the shape of space-time. In this way, geometry arises from quantum relationships, not the other way around. This could explain why space-time appears smooth and continuous at macroscopic scales, even though at the quantum level, it may be discrete or non-existent. This paradigm shift also alters how we think about the Big Bang. Traditionally, we imagine it as a singular point from which all space and time emerged. But if space and time are not fundamental, then the Big Bang may not have been a physical explosion at all. It could have been a phase transition in an underlying quantum information system, a kind of cosmic reboot. In this model, the universe didn't expand into space. Space expanded into the universe, emerging from correlations and symmetries at a deeper level. Time, too, may not have flowed before this moment, because it didn't exist. There was no before in any meaningful sense, only a state of pre-geometry, a quantum fog from which order gradually emerged. These ideas are difficult to grasp, because they require us to abandon not just our models, but our intuitions, our language, our metaphors. We are used to thinking of the universe as a thing, an object in which we live. But if the universe is a computation, then we are not inside it the way a character is inside a room. We are part of the process, threads in the tapestry, subroutines in the code. This reconceptualization also reshapes scientific dialogue. No longer can we afford to divide physics into tidy silos, quantum mechanics over here, general relativity over there. The most promising approaches to quantum gravity, such as string theory and loop quantum gravity, demand a synthesis of ideas, a blending of disciplines that once seemed distant. Concepts from information theory, computer science and topology are now as relevant to cosmology as mass and energy once were. The boundaries between disciplines are dissolving, just as the boundaries between space and information may be. And with this shift comes a new generation of physicists and thinkers who are not bound by tradition, who are willing to entertain radical models, not out of rebellion, but out of necessity. The evidence demands it. The puzzles, dark energy, dark matter, the nature of time, the origin of entropy, the arrow of time, the singularity at the heart of a black hole, require tools we have not yet fully developed. But this new perspective is not without resistance. Some physicists are skeptical of ideas like the holographic principle, arguing that they are mathematically elegant but experimentally inaccessible. Others worry that the focus on theory is drifting too far from observation, that we may be losing touch with the empirical spirit that built modern science. These are valid concerns. Science thrives on testable predictions, and theories must eventually be anchored in data. But it is also true that many of the greatest revolutions in physics began as thought experiments, mathematical insights, or radical reimaginings. Einstein's theory of relativity began as a contradiction between Newtonian mechanics and Maxwell's equations. Quantum mechanics emerged from inexplicable anomalies in blackbody radiation and atomic spectra. In each case, the problem was not that the data was wrong, but that the perspective was limited. The same may be true now. The universe hasn't changed, but perhaps our way of seeing it must. And in this context, quantum mechanics takes on a new and central role. Once considered merely the theory of the very small, it is now seen as a foundational pillar of the cosmos. Quantum fluctuations seeded the structure of the universe during inflation. Quantum fields underlie all matter and force. Quantum entanglement may be the key to understanding space-time itself, and yet, quantum theory remains profoundly mysterious. Its probabilistic nature, its observer-dependent realities, its dualities and paradoxes, all hint at a deeper structure we do not yet comprehend. We know how to use quantum mechanics with astonishing precision, yet we don't really know what it means. Is the wave function real? Does consciousness collapse it? Are many worlds splitting off with every decision? These questions are no longer confined to the realm of interpretation. They now have implications for cosmology, for information, for the fate of the universe. Indeed, as we grapple with the holographic universe and quantum spacetime, the boundary between physics and philosophy becomes thinner. We are no longer just measuring particles, we are asking what it means to be real. We are no longer just tracking expansion, we are asking what it means for space to exist. This shift in perspective does not weaken science, it deepens it. It makes it more honest, more daring, more creative. It invites us to imagine models that do not rely on our everyday experience, because the universe is not obliged to conform to human intuition. The universe is not here for us to understand easily.
There are moments in science when a discovery not only changes what we know, but forces us to question how we know anything at all. Moments when the ground shifts beneath the most foundational assumptions and we are left staring into a deeper, stranger reality than we ever imagined. For centuries, cosmology has been a quest to explain the origin, structure, and fate of the universe, a journey that has taken us from the geocentric spheres of ancient thinkers to the expanding universe of the Big Bang, from Newton's predictable cosmos to Einstein's curved spacetime, and from galaxies and stars to quantum foam and black holes. Each breakthrough has refined our map of reality, but in recent years we've arrived at a strange and disorienting frontier. Here, the universe does not behave like a neat machine with a single clear story. Instead, it begins to look like a mystery layered with paradox, probability, and perspective. The latest discoveries have not merely added details to the cosmic picture, they've torn holes in the canvas, and through those holes we glimpse something else entirely, a universe that might be one of many, a simulation within a deeper system, or a fleeting shadow of a reality far richer and more complex than we can yet comprehend. One of the most unsettling revelations of modern cosmology is that the universe is not what we thought it was, not in structure, not in behavior, and perhaps not even in meaning. For decades, scientists believed that the universe was composed primarily of matter and governed by the four known fundamental forces, but the discovery of dark matter and dark energy overturned this view completely. We now know that the matter we can see, everything from galaxies to atoms, accounts for less than 5% of the universe. The rest is invisible, mysterious, and almost completely unexplained. Dark matter, which makes up about 27%, exerts gravitational effects but does not emit or absorb light. Dark energy, which accounts for roughly 68%, is even more baffling. It drives the acceleration of the universe's expansion, acting like a repulsive force woven into the vacuum of space itself. These discoveries didn't just challenge old theories, they revealed that we are fundamentally ignorant of what most of the universe is made of. But even as we grappled with the strangeness of the dark universe, new models emerged that pushed the boundaries even further. One of the most radical is the multiverse theory, the idea that our universe is just one of many, perhaps an infinite number, each with its own physical laws, constants, and initial conditions. This concept emerged naturally from inflationary cosmology. According to the theory of cosmic inflation, the universe underwent a brief but massive expansion just after the Big Bang. In some models, this inflation never completely stops but continues in other regions, creating bubble universes, each one a separate cosmos, potentially with different dimensionality, particle types, and forces. We might live in a universe with the specific properties needed for life, not because those properties were chosen or fine-tuned, but because in an infinite multiverse, such conditions will inevitably arise somewhere. This is the anthropic principle at a cosmic scale. We observe a universe suited for life because only in such a universe could we exist to observe it. The multiverse idea is not without controversy. It stretches the scientific method to its limits, since these other universes may be forever beyond observational reach. Yet it solves deep problems in physics, including why certain constants seem so improbably well-tuned for life. It also challenges our notions of uniqueness, meaning, and probability. If there are infinite versions of you, some making different choices, some experiencing different outcomes, what does it mean to be you? What does it mean for anything to be real, if every possible reality is realized somewhere? These are not merely abstract puzzles. They touch on ethics, identity, and consciousness itself, and they open the door to a theory even more unsettling, the simulation hypothesis. Popularized by philosopher Nick Bostrom and echoed by scientists and technologists like Elon Musk, the simulation hypothesis suggests that what we perceive as reality might be an artificial construct, an incredibly advanced simulation created by an intelligence far beyond our own. The logic is deceptively simple. If it becomes possible for civilizations to run high-fidelity simulations of conscious beings, and if they do so frequently, then simulated realities would vastly outnumber base realities. Statistically, it becomes far more likely that we are inside one of those simulations than in the original real universe. What we call physics may simply be the rules of the simulation. What we call randomness may be a form of procedural generation. The laws of nature could be algorithms. Quantum indeterminacy might reflect computation limits. The speed of light could be a processing cap. These ideas were once relegated to science fiction, but they are now being taken seriously by researchers in quantum mechanics, information theory, and digital physics. One piece of evidence, or at least philosophical motivation for the simulation hypothesis, is the holographic principle, which, as discussed earlier, suggests that the universe might be fundamentally two-dimensional, with our three-dimensional experience being a projection. This ties into ideas from quantum information theory, where reality may be best described not in terms of particles and forces, but bits and qubits. If space and time themselves emerge from entanglement patterns, then our everyday world is not the foundation of reality, but its result. In this view, we are not seeing reality as it is, but as it appears after a kind of cosmic rendering process. And here the boundary between physics and computation begins to blur. The universe might be not a place but a process, not a thing but an unfolding event. These perspectives are not only mind-bending, they are transforming how we think about science itself. No longer is the goal simply to describe what we see. Now we must also ask what filters and frameworks are shaping our perception. Are the questions we're asking constrained by the structure of the human mind, the architecture of consciousness, the bias of biology? Could it be that certain truths are fundamentally inaccessible to us, not because they are unknowable in principle, but because they lie outside the cognitive and perceptual toolkit we evolved for survival on Earth? This possibility humbles us. It forces us to acknowledge that we might be like ants trying to understand a cathedral, interpreting grand patterns through the lens of small experience. And yet, even within these disorienting models, a deeper realization is emerging, one that recenters the human experience, not as cosmic rulers or divine creations, but as participants in a far greater story. If the universe is a multiverse, then the fact that we are here at all means something. If reality is a simulation, then the simulation is capable of producing conscious, questioning beings who can love, dream, create, and ask why. If space and time are emergent, then the emergence of awareness may be one of the most significant events in the cosmos. And if information is the most fundamental layer of reality, then every thought, every feeling, every observation adds to the cosmic record, not because the universe cares, but because caring is part of what we contribute to the universe. This shift from a mechanical to a participatory model of the cosmos is perhaps the most unexpected twist of all. For centuries, science has tried to remove the observer from the equation. The universe, we were told, is indifferent, objective, out there. But quantum mechanics teaches us that observation matters, that particles don't even settle into a definite state until they are measured. Some interpretations go further, suggesting that consciousness collapses the wave function, that the observer plays an active role in shaping what is real. This doesn't mean we create reality with our minds in a magical sense. but it does mean that any complete theory of the universe must include the observer, not just as a passive recipient of data, but as a co-constructor of phenomena. In this light, our place in the cosmos is both diminished and elevated. We are not the center of creation, we are not even significant in terms of mass or volume, but we are significant in a different way. We are the means through which the universe becomes aware of itself. We are the way reality reflects, questions and transforms. If the universe is a simulation, then we are its meaning makers. If the universe is a multiverse, then we are the version where curiosity evolved. If the universe is a hologram, then we are the ones who ask what lies beyond the screen. The twist, then, is not just scientific, it is existential. The more we discover about the universe, the more it resists closure. Every explanation reveals deeper mysteries. Every answer births more questions. We started this journey hoping to find a neat diagram, a final theory, a cosmic equation, but instead, we have found a living labyrinth, an open-ended process, a strange loop where the deeper we go, the more we discover about ourselves. The cosmos is not a book with an ending, it is a story that rewrites itself as it is read, and in reading it, we become part of it. Perhaps this was always the case. Perhaps the unexpected twist is that there was never a final answer to be found, only better questions to be asked. And maybe, in the end, that is what defines intelligence, life and meaning in a universe like ours. Not certainty, not power, but the courage to wonder, to explore, to imagine, to change. So we continue, on this small planet orbiting a modest star in one galaxy among trillions. We build telescopes and run simulations. We debate paradoxes and rewrite equations. We dream of other worlds and simulate our own. And all the while, the universe watches through our eyes, thinks through our minds, feels through our hearts. We are the twist in the story, the part the universe did not expect, the part that asks what does it all mean. And though the answer may never come, the asking itself may be the most meaningful thing of all. Despite the stunning breakthroughs of recent decades, despite peering back in time with the James Webb Space Telescope, detecting gravitational waves, mapping the cosmic microwave background in exquisite detail, and developing revolutionary new theories that reimagine the structure of space and time, cosmology stands at a new frontier, marked not just by discovery, but by a daunting array of unresolved questions. The universe has given up many of its secrets, but it continues to withhold its most profound truths. As our models of the cosmos become more sophisticated, so too do the challenges we face, from the nature of dark energy and dark matter, to the origin of time itself, to the possible existence of other universes, and the limits of our observational reach. The scientific journey is entering a phase where the obstacles are no longer just technological, they are conceptual, philosophical, and deeply intertwined with the very nature of knowledge. Perhaps the most obvious challenge facing cosmologists today is the incomplete picture of the universe's composition. Roughly 95% of the universe is made of dark energy and dark matter, components we cannot directly observe or explain. Dark matter reveals its presence only through gravitational effects, the way galaxies rotate, the way light bends around clusters, the large-scale structure of the universe. And yet, despite decades of effort, we have not identified the particle or mechanism responsible for dark matter. Is it a WIMP, weakly interacting massive particle, an axion, a sterile neutrino, or is it not a particle at all, but a failure in our understanding of gravity? Competing theories such as modified Newtonian dynamics, MUND propose alternatives to dark matter, but they struggle to match the consistency of cold dark matter models across cosmic scales. Until we detect dark matter directly, or definitively disprove it, this gap will remain one of the most significant roadblocks in cosmology. More elusive still is dark energy, the mysterious force accelerating the expansion of the universe. Discovered in 1998, through the study of distant supernovae, dark energy now dominates the energy budget of the cosmos, and yet we have no idea what it is. Is it a cosmological constant, as Einstein once proposed, and later rejected? Is it a dynamic field quintessence that evolves over time? Is it an artifact of higher dimensions, or a clue that gravity behaves differently at large scales? These are not minor details. The answers could redefine our understanding of fundamental physics, and determine the fate of the universe, whether it will expand forever, tear itself apart, or eventually slow and collapse. Solving the mystery of dark energy requires a level of precision and scale in observation that current instruments are only beginning to approach, which leads to the second major challenge: technological limitations. Our greatest insights into the universe have come from space-based telescopes, like Hubble, Planck, and now James Webb.
These instruments have transformed astronomy, but even they have limits. They are constrained by the wavelengths they can observe, the size of their mirrors, the length of their missions, and the interference of Earth's environment. Many of the most pressing questions about inflation, dark energy, the early moments of the Big Bang, and the nature of black holes require next-generation technology. For example, detecting the faint signal of primordial gravitational waves, ripples from the first fraction of a second after the Big Bang, requires instruments far more sensitive than anything currently in operation. Projects like the Laser Interferometer Space Antenna, LISA, aim to detect gravitational waves from space, targeting frequencies inaccessible to ground-based detectors like LIGO. LISA will be capable of observing mergers between supermassive black holes, as well as background signals from the early universe, offering an entirely new window into cosmic history. Similarly, missions like Euclid and the Nancy Grace Roman Space Telescope, both aimed at studying dark energy and the large-scale structure of the universe, will provide data orders of magnitude more precise than existing surveys. These missions are designed to map the distribution of galaxies across billions of years of cosmic time, measuring weak gravitational lensing, baryon acoustic oscillations, and the expansion history of the universe. By tracking how structures have evolved, scientists hope to distinguish between competing models of dark energy and gravity, but even these projects are stepping stones. To truly answer the next generation of cosmological questions, we will need observatories, the size of cities in space, telescopes that can see in energy ranges we haven't yet accessed, and detectors cooled to near absolute zero to eliminate noise. Another formidable challenge lies in the interpretation of data. As we collect more information from space particle detectors and gravitational wave observatories, the complexity of the data increases exponentially. We are no longer dealing with images or simple spectra. We are analyzing multidimensional datasets that require machine learning, artificial intelligence, and new statistical frameworks to interpret. This shift has created a growing need for computational cosmology, where supercomputers simulate the evolution of the universe across billions of years, tracking the movement of trillions of particles under gravity and other forces. These simulations are crucial for testing theories of structure formation, for matching observational data to theoretical predictions, and for exploring scenarios we cannot observe directly. But they also raise new questions. How do we validate a simulation? What biases are baked into the algorithms? Are we mistaking model-dependent outcomes for physical truths? And yet, even as technology and computation advance, some questions remain stubbornly out of reach, not because of limitations in tools, but because of fundamental barriers in measurement. The cosmic microwave background, for example, represents the farthest back in time we can see using light, about 380,000 years after the Big Bang. Before that moment, the universe was opaque. To go further, we would need to detect neutrinos, or gravitational waves from the primordial universe, signals so weak and elusive, they require revolutionary detection methods. Similarly, we may never directly observe the interior of a black hole, where general relativity breaks down and quantum gravity is needed. These are not technological challenges in the usual sense. They are epistemological limits, boundaries on what we can know based on how the universe presents itself to us. The challenge for future science is not just to build better tools, but to find clever new ways of asking questions, constructing experiments, and extracting meaning from silence. In the face of these challenges, how do scientists plan to move forward? One approach is the integration of disciplines. Cosmology can no longer be separated from particle physics, quantum field theory, information theory, or even philosophy. Projects like CERN's Large Hadron Collider, LHC, while not telescopes, contribute directly to cosmology by searching for particles that could explain dark matter or reveal physics beyond the standard model. Similarly, the study of quantum entanglement and entropy in black holes is feeding into theories of quantum gravity and emergent spacetime. The next great breakthrough in understanding the universe's structure may come not from a new telescope, but from a new equation, a new symmetry, or a new interpretation of quantum mechanics. There is also a growing recognition of the need for global collaboration. Missions like LISA, the Square Kilometre Array, SKA, and future moon-based observatories are international efforts, drawing on the expertise, funding, and cooperation of dozens of countries. The scale of these projects, and the questions they seek to answer, demands a planetary response. No single nation can unlock the universe alone. As we look to establish outposts on the Moon and Mars, there is talk of building telescopes on the far side of the Moon, shielded from Earth's noise, where they could observe in radio frequencies with unprecedented clarity. These are long-term goals, but they reflect a growing ambition to take science not just deeper but wider, to make it a collective human endeavor. On a cosmic scale, and beyond the purely scientific hurdles, there is the philosophical challenge of humility. We are beginning to understand that the universe may not be designed to be fully knowable. It may contain layers of reality beyond our conceptual reach, forms of intelligence or order that escape detection, patterns that emerge only at scales or energies we cannot probe. In response, some scientists are calling for a new epistemology, a way of doing science that embraces uncertainty, that sees knowledge not as static truth, but as an evolving map of approximation. This does not mean abandoning rigor or evidence. It means recognizing that even our best theories are stepping stones, not destinations, and so the road ahead is both daunting and exhilarating. The next chapter in cosmology will not be written with a single telescope or paper, but with a mosaic of efforts, each addressing a piece of the puzzle. We will need new missions, infrared observatories that go deeper than Webb, gravitational wave detectors, sensitive to the earliest epochs, dark matter labs buried deep in ice or rock, radio arrays that span continents. We will need new theories, frameworks that unify quantum mechanics and gravity, that explain dark energy, not as an afterthought, but as a natural feature of the cosmos. We will need new minds, scientists unafraid to question dogma, engineers who can dream and build what doesn't yet exist, and thinkers who can translate the math into meaning. Above all, we will need endurance. The journey to understanding the universe is not a sprint, but a generational relay, a chain of questions and insights passed from one era to the next. Each discovery opens new doors, but also reveals more corridors, more layers, more unknowns. This is the paradox of science. The more we know, the more we realize how much we don't. But that is not a flaw, it is the engine of progress. The unanswered questions are not walls, they are invitations. What caused the Big Bang? What is the true nature of time? Are there other universes beyond our own? Is the universe a computation, a projection, a simulation, or is it something more strange and beautiful than any metaphor we can imagine? These are the challenges that await the next generation, and even if we never find all the answers, the act of seeking them will transform, making us not just better scientists, but better stewards of wonder. In the darkness between the stars, we are learning to ask again, and in asking, we move forward, not toward a final truth, but toward a deeper way of seeing, toward a future where the universe is not just a subject to be studied, but a mystery to be lived. In the vast theater of the cosmos, we have journeyed from myth to measurement, from stars etched in clay tablets, to quantum fields scribbled on chalkboards. Along this journey, we've dismantled illusions, faced paradoxes, and built machines capable of reaching far beyond the capacity of human senses. We've found that Earth is not the center of anything, that time is not universal, and that matter is not what it appears to be. And now, as we stand at the edge of everything we know, cosmology confronts its most formidable question: is there a final boundary to understanding the universe, or is the cosmos an infinite recursion of mystery, forever expanding beyond the limits of thought? At the heart of this confrontation lie the latest competing theories of the universe, models so profound and complex, they test not only our instruments, but our imagination. These are not mere refinements of older ideas, they are radical attempts to reconcile contradictions that sit at the foundation of physics, and none is more pressing than the task of unifying general relativity with quantum mechanics, Einstein's smooth geometric world of curved spacetime and gravity, and the probabilistic pixelated realm of quantum fields and uncertainty. These two pillars of modern physics describe their respective domains with astonishing accuracy, yet where they meet, at black hole singularities, at the Big Bang, and in attempts to describe the universe as a whole, they collapse into mathematical chaos. Resolving this conflict is not just a technical challenge, it is the final confrontation between two visions of reality. Among the most discussed unification frameworks is string theory, the idea that all fundamental particles are not point-like, but tiny vibrating strings, each mode of vibration corresponding to a different particle. String theory is elegant, mathematically rich, and potentially unifies all known forces, including gravity. It naturally incorporates extra dimensions, up to 10 or 11 in some models, and provides a consistent quantum theory of gravity. But it comes with a steep price. It predicts not one universe, but a vast landscape of possible universes, perhaps 10 circumflex 500 or more, each with its own physical constants and laws. This leads naturally into multiverse theories, where our observable universe is just one pocket among countless others. Critics argue that string theory lacks falsifiability, that it's more mathematics than physics, but its defenders see it as a necessary leap, a new language in which the universe must eventually be written. In contrast, Loop quantum gravity takes a different approach. It preserves the principles of general relativity, but quantizes spacetime itself. Instead of being a smooth continuum, space is made of discrete loops or quanta, woven together like a spin network. This theory predicts a minimum unit of volume, resolving singularities, by preventing infinite densities. In some models, the Big Bang is replaced by a big bounce, where a previous contracting universe gave way to ours. Loop quantum gravity is less grand in scope than string theory, but more conservative in assumptions. It focuses on background independence, preserving the idea that spacetime is dynamic and relational. While it hasn't yet united all forces, it offers testable predictions about the early universe, black holes, and the quantum geometry of space. Beyond these, emergent gravity and entropic gravity propose that gravity is not a fundamental force, but an emergent phenomenon, like temperature or pressure, arising from the statistical behavior of microscopic degrees of freedom. In these models, spacetime itself emerges from more fundamental entities, information, quantum entanglement, or even thermodynamic principles. This radically repositions gravity, not as a curvature of geometry, but as a consequence of entropy gradients, or quantum information networks. These ideas draw on the holographic principle, suggesting that all information in a volume of space is encoded on its boundary. This viewpoint has gained traction from the AD-CFT correspondence, where a higher dimensional theory of gravity is equivalent to a lower dimensional quantum field theory without gravity. If true, this could mean that the universe we experience is a kind of projection from a deeper information-based reality. And yet, for all their mathematical beauty, these theories remain theories, untested in the crucible of experiment. The greatest hurdle we face is not inventing models, but testing them. Many of the effects predicted by quantum gravity, such as spacetime discreteness, Lorentz invariance violations, or quantum black hole evaporation, lie far beyond our current experimental capabilities. We cannot yet build particle accelerators that reach the Planck scale, nor can we probe the interior of a black hole, but scientists are finding clever workarounds. For instance, by studying the cosmic microwave background for non-Gaussianities, or subtle quantum signatures, we may glimpse traces of Planck-scale physics. Likewise, gravitational wave detectors, like LIGO and future observatories, like LISA, may detect echoes or quantum corrections from black hole mergers. High-precision cosmological surveys may reveal deviations in the growth of structure, or anomalies in cosmic expansion. These are indirect tests, but they are the bridges we must build to cross the chasm between theory and evidence. Still, the most profound debate remains philosophical. Will we ever find a true boundary? Not just a spatial boundary, an edge of the universe, but a boundary in knowledge, a place where explanation stops, where the veil of mystery remains unlifted. Historically, science has overcome apparent boundaries with deeper models. Newton explained the motion of the planets, Einstein redefined gravity, quantum mechanics resolved blackbody radiation, and atomic spectra. Each time we thought we hit a wall, it turned out to be a door, but perhaps this time is different. The universe may be constructed in a way that makes certain truths fundamentally inaccessible, either because of the limits of observation, or because of the limits of cognition itself. If space-time is emergent, then asking what it is made of may be like asking what pixels are made of in a video game. If time is not fundamental, then seeking a beginning may be a category error. If we are in a multiverse, then many of the properties we observe may be environmental, unexplained because they are selected rather than caused. This does not mean we should give up. It means we must rethink what it means to understand. Perhaps cosmology's true destination is not a final theory, but a deeper humility, an awareness that the map is never the territory, that the theory is never the thing. Yet even in uncertainty, science advances. The search for quantum gravity has already led to mathematical tools that are transforming other fields: entanglement, entropy, gauge gravity duality, tensor networks. These ideas are rippling outward, informing condensed matter physics, quantum computing, and even machine learning. The quest to understand the cosmos is feeding back into technology, just as the tools we build for exploration are reshaping how we think. And what of the future? The future of cosmology will be defined not just by big questions, but by bold instruments. In the next few decades, we will launch the Nancy Grace Roman Space Telescope, expanding our ability to study dark energy in exoplanets. We will build LISA, a space-based gravitational wave observatory that will explore the invisible symphony of massive black hole mergers. We will construct the Square Kilometre Array, the world's largest radio telescope, capable of probing the dawn of cosmic structure. We will push quantum sensors to new limits, detecting ever fainter signals from the early universe. And we will harness AI and machine learning to analyze datasets so vast that human pattern recognition is no longer enough. Each of these missions will chip away at the unknown, revealing new anomalies, new contradictions, new glimpses into the deep architecture of the cosmos.
But cosmology's future is not just in the stars, it's in the mindset of those who explore them. The next generation of physicists will not only need technical brilliance, but conceptual courage. They will need to question assumptions so deeply rooted they feel like facts. They will need to cross disciplines, blend mathematics with philosophy, and wield intuition alongside computation. They may come from physics, or computer science, or neuroscience, or fields we haven't yet invented. What binds them will not be a specific question, but a shared commitment to inquiry, a refusal to settle for the merely plausible. And so the final confrontation is not between theories, but between the known and the unknown, between the comfort of answers and the challenge of deeper questions, between a universe that we can describe and a reality that remains always just out of reach. It is the moment when science becomes not just a method but a mirror, a way of seeing not only the cosmos but ourselves within it. We are not passengers on a ship sailing through space. We are part of the ocean. We are the eyes with which the universe sees itself. And in every equation we write, every particle we collide, every photon we catch from the edge of time, we are continuing the ancient journey, one that began with wonder and ends, not in certainty but in awe. The future may not give us a final theory. It may not give us a boundary to touch or a theory of everything neatly wrapped in mathematical elegance, but it will give us something more powerful, the unfolding story of a species learning, piece by piece, how to ask the right questions, and in that asking, we will become something greater than we are today, not because we have conquered the cosmos, but because we have learned how to live within its mystery. In the confrontation between knowledge and ignorance, between light and darkness, between theory and truth, we will not find an ending. We will find the next horizon, and beyond it more stars. Somewhere beyond the orbit of Neptune, far past the icy edges of the Kuiper Belt, two tiny spacecraft, Voyager 1 and Voyager 2, drift silently through the interstellar void. Launched over 40 years ago, these emissaries from Earth carry with them golden records, artifacts of sound and music, images of humanity, greetings in dozens of languages. They are not likely to be found anytime soon, perhaps never, but their purpose is not only to communicate with others, they are messages to ourselves, a declaration that even in the face of the infinite, we dared to wonder, to explore, and to reach beyond what we could grasp. In those golden discs lies the moral heartbeat of science, the belief that knowledge is worth seeking, that mystery is not to be feared, and that curiosity is not a luxury. It is essential to who we are. At its deepest level, the exploration of the cosmos is more than an intellectual exercise. It is a moral act. It is an affirmation that truth matters, that effort in the name of understanding is valuable regardless of outcome, and that the unknown is not a void to be filled with fear, but a space to be met with wonder. The universe does not care about our beliefs, our borders, or our politics. It does not reward ego, nor does it punish arrogance. It simply is, vast, ancient, and indifferent. And yet, in confronting that indifference, we find something profound. We find that the act of looking up, of questioning, of building and testing, and revising, is not just how we learn. It is how we evolve. It is how we rise beyond the limitations of the moment and connect with something greater than ourselves. Curiosity is the engine of scientific progress, but it is also more than that. It is a form of courage. To be curious is to admit you do not know, to acknowledge that there is more to learn, and to open yourself to uncertainty. That mindset, humble, patient, relentless, is the foundation of all great discoveries. From Newton watching an apple fall to Einstein, imagining riding alongside a beam of light, from Vera Rubin, measuring galaxy rotation curves, to the teams who built the James Webb Space Telescope, the same flame burns through time, the desire to understand. And yet, curiosity alone is not enough. It must be married to discipline, to skepticism, to the slow and rigorous process of hypothesis and evidence. Scientific progress is not a straight line. It is a spiral, one that loops through error, correction, insight, and deeper questions, but it always moves forward. And the fuel for that movement is the simple, often childlike impulse to ask, what if? Cosmic exploration sharpens this impulse to a fine point. The universe is not merely large, it is fundamentally strange. Its laws are not always intuitive. Light behaves both like a wave and a particle. Time slows near massive objects. Particles pop in and out of existence in a vacuum. Galaxies are held together by matter we cannot see. The vast majority of the cosmos is invisible, undetectable, mysterious, and yet the more we learn, the more patterns we find. The same elements that formed in ancient stars also form our bones. The same forces that shape galaxies guide the flight of apples to the ground. In studying the universe, we are studying ourselves. And the deeper we go, the more we discover that our existence is not a cosmic afterthought, but an emergent property of the very processes we seek to understand. This leads to one of the most humbling and powerful lessons of cosmic exploration: the balance between knowledge and mystery. Science does not exist to eliminate mystery. It exists to navigate it. To explore is not to extinguish the unknown, but to learn how to live alongside it with clarity and integrity. Every time we solve one riddle, a dozen new ones emerge. We mapped the solar system, only to find new planets and asteroids. We described the atom only to discover subatomic particles and quantum fields. We explained gravity, only to encounter dark energy accelerating the universe's expansion. The unknown is not a problem to be solved. It is a partner in dialogue, and that dialogue teaches us to be both confident and cautious. Confident in our ability to learn, to test, to build, and to understand, but cautious in our conclusions, open to being wrong, and respectful of what we do not yet grasp. That humility is not weakness, it is wisdom. It is what allows science to grow. Unlike dogma, science admits its imperfections. Unlike ideology, it revises itself in the light of new evidence. It does not cling to certainty for comfort. Instead, it embraces doubt as a tool. That is a moral lesson, not just a methodological one. In a world where misinformation spreads rapidly, where fear can drown out facts, and where polarization thrives on false certainty, the mindset of science, curious, humble, evidence-driven, is more important than ever. It teaches us to slow down, to examine our assumptions, to value truth over pride, and to trust the process even when it is slow or uncertain. These values are not confined to labs or observatories. They are principles we can apply to politics, education, relationships, and personal growth. Moreover, exploring the cosmos reminds us of something vital. We are one species on one planet. The overview effect, described by astronauts who have seen Earth from orbit, is a profound shift in perspective. From space there are no borders, no nations, no wars, only a single fragile world suspended in darkness. Carl Sagan called it the pale blue dot, a lonely speck in a vast cosmic arena, but that dot contains everything we've ever known. Every human, every history, every hope and heartbreak. And when we explore space, we do so not as Americans or Russians, not as theists or atheists, not as the left or the right, but as human beings, as curious, imperfect, dreaming creatures who dare to ask where we come from and where we're going. This perspective is a source of hope, because it means that even in our divisions, we have a shared destiny. The effort to explore space, whether through telescopes, probes, or potential human missions, requires cooperation, shared knowledge, and mutual trust. It is a kind of planetary therapy, reminding us that what unites us is far greater than what divides us. And in an age where global challenges, from climate change to pandemics, to nuclear proliferation, threaten our future, that unity of purpose is not just inspiring, it is essential. The moral takeaway, then, is clear: exploring the universe is not about escape. It is about understanding. It is about growing up as a species, about recognizing that we are part of a larger story, one that began long before us, and will continue long after us. But for this brief moment, we are the consciousness of the cosmos, the universe made aware, and that awareness carries responsibility to protect our planet, to care for each other, to preserve the miracle of life in a universe where, as far as we know, it is rare, to build societies that value truth, creativity, empathy, and vision, to be worthy of the stars we now reach for. It also means learning to live with wonder, not as a fleeting emotion, but as a guiding principle. Wonder is the bridge between science and spirit, not religion, necessarily, but reverence. Reverence for the complexity of the natural world, for the improbability of existence, for the quiet power of atoms, and the explosive birth of stars, for the deep time that connects us to every particle, and the fleeting present that allows us to feel, to think, to ask. Wonder reminds us that knowledge is not just about power, it is about connection, that to know the universe is not to conquer it, but to belong to it more fully. And so the journey continues. We send robots to Mars, and probes to the outer solar system. We build gravitational wave detectors and quantum computers. We stare into the past through deep space telescopes and run simulations of alternate realities. We debate the multiverse, ponder the nature of time, and chase the ghost of a theory of everything. But beyond all the equations, all the funding proposals and conference papers, lies a truth that cannot be graphed, that what we are really searching for in the stars is not just other planets, or alien life, or the birth of the universe. We are searching for ourselves. We are searching for our place in the story, our role in the pattern, our meaning in the mosaic, and in doing so, we are becoming the kind of beings who deserve to ask such questions, the kind who build not just machines, but meaning, the kind who, when given a spark of curiosity, turn it into a fire of discovery, the kind who understand that mystery is not the end of knowledge, it is its beginning. So let the mystery remain, let it challenge us, inspire us, humble us. Let it teach us that the pursuit of truth is not just an intellectual exercise, it is a moral calling. To be curious is to be alive, to explore is to be human, and to wonder, always, is to touch the edge of the eternal. That is the lesson of the cosmos, not that we are small, but that we are rare, not that we are lost, but that we are capable, and not that we must find all the answers, but that we must never stop asking the question. In the grand expanse of cosmic inquiry, we have followed questions that led us through galaxies and gravity wells, across black holes, and into the realm of quantum fuzz. We've built theories, launched instruments into space, peered into the faint radiation of the universe's birth, and stretched our imaginations to their limits, only to discover that the more we uncover, the more we realize how much we do not know. Every horizon we reach reveals another beyond it, like an eternal cosmic mirage. The universe, it seems, is not designed to offer finality, but to reward persistence. In this pursuit, we find ourselves standing before a philosophical crossroads. Should we continue pressing toward a final closed conclusion, a unified theory, a single narrative that wraps up all mystery in a tidy bow? Or should we accept, and even embrace, that some questions may forever remain open-ended, that the universe might not be a riddle to be solved, but a vast, evolving conversation in which we are participants, not conquerors? To leave the mystery open-ended is not a failure of science. It is a celebration of science's deepest strength, its ability to remain curious, to resist dogma, and to live in the tension between what is known and what is possible. Scientific progress is not measured by how many answers we have collected, but by the quality of the questions we are still brave enough to ask. In cosmology, perhaps more than any other discipline, is built upon this principle. Every theory that once seemed to close the case has eventually been upended, revised, or expanded. Newton's laws gave way to Einstein's relativity, which in turn bends and stretches under the pressure of quantum mechanics. The Big Bang model, once considered a complete origin story, now opens into inflationary theory, multiverse hypotheses, and quantum fluctuations from a pre-geometric state. Dark matter and dark energy, terms we use to label our ignorance, remind us that even our most successful models are built on an incomplete understanding of the cosmos. This is not to say we should abandon the pursuit of finality. The quest for a theory of everything, a framework that unites gravity with quantum mechanics, that explains the origin of time and the arrow of entropy, that accounts for the values of fundamental constants and the very structure of reality, is one of the most noble and difficult challenges in science. But perhaps we must shift how we think about such a theory. Instead of a definitive endpoint, it may be more like a milestone on an endless road, a powerful model that explains much, but still leaves room for surprises. In this way, even the ultimate theory would be less a final destination and more a vantage point, offering a clearer view of the next mysteries that await. There is great value in leaving questions unanswered. Unanswered questions are an invitation. They spark creativity, fuel innovation, and keep the human spirit awake and alive. Think of the role uncertainty has played in scientific history. When Galileo turned his telescope to the sky and saw moons orbiting Jupiter, he didn't close a chapter, he opened one. When Edwin Hubble discovered the expansion of the universe, he did not offer a conclusion, he set cosmology ablaze. When dark energy was discovered in the 1990s, it wasn't the end of a theory, but the beginning of 100 new ones. In every case, mystery did not halt progress, it accelerated it. Unanswered questions are the lifeblood of scientific progress, and they serve an even deeper human purpose. They remind us to stay humble. Humility is a vital virtue in the face of the cosmos. When we contemplate a universe 13.8 billion years old, and more than 93 billion light-years across, teeming with perhaps 2 trillion galaxies, each with billions of stars, and countless planets, we are forced to reevaluate our place in it. And yet, within this vast arena, we are the only known entities who reflect, who question, who build tools to measure the unseeable and imagine the unimaginable. That alone is worth celebrating. We are not small in a way that makes us meaningless.
We are rare in a way that makes us precious. The fact that we ask questions at all, that we even know there are mysteries to ponder, is itself a triumph of evolution, culture and consciousness. To leave the mystery open is to honor that capacity, to say we may not know everything, but we know enough to care. Let us then reflect on some of the biggest takeaways from our journey through the cosmos. First, we've learned that the universe is not static or simple. It is dynamic, complex and filled with hidden layers. From the stretching of space in the aftermath of the Big Bang, to the silent expansion driven by dark energy, from the quantum foam bubbling at the Planck scale, to the majestic structure of the cosmic web, the universe reveals a reality far stranger and more beautiful than any mythology ever imagined. Second, we've learned that the very fabric of reality, space, time, energy, and information, may not be fundamental. These may be emergent properties, rising from deeper laws we do not yet understand. Third, we've seen that our place in the universe is both insignificant in scale and profound in meaning. We are made of stardust, connected to the death of ancient stars, in the entropy of black holes, incapable of contemplating our own origins. We've also come to see that our tools are only as good as our questions. Our telescopes, satellites, detectors, and simulations are magnificent, but they must be guided by imagination, insight, and courage. The future of cosmology lies not just in better instruments, but in better minds, minds that can transcend current paradigms, that can weave together physics and information theory, quantum mechanics and geometry, entropy and consciousness. The questions we now face, about dark matter, dark energy, the multiverse, the holographic nature of space, the simulation hypothesis, and the unification of forces, are not just puzzles to be solved. They are doorways to new ways of thinking. And what about final thoughts on the infinite possibilities of space? Perhaps the most profound realization from modern cosmology is that the universe is not a closed system. It is not an object with edges, or a timeline with a tidy beginning and end. It is an unfolding process, a dance of energy and structure that continually surprises us. Within it may exist other universes, other forms of life, other laws of physics. Time may not be linear, space may not be continuous, dimensions may exist beyond those we can perceive. The cosmos may be infinite in extent, in depth, in complexity, or it may be finite, yet without boundary, like the surface of a sphere. We don't know, and that's exactly why we must continue exploring. To leave the mystery open-ended is to remain in dialogue with the universe. It is to recognize that we are not separate from it, but embedded within it, that the questions we ask are not just about stars and particles, but about identity, purpose, and connection. When we wonder what caused the Big Bang, we are also wondering about the nature of beginnings. When we study entropy in time's arrow, we are also asking about change and death. When we imagine alien civilizations, we are reflecting on our own loneliness, our potential, and our fear. Space is not empty, it is full of meaning, if we are willing to see it. In that sense, the mystery is not a void, it is a mirror. The cosmos reflects us back to ourselves, not as the center of creation, but as a curious, conscious part of it. It challenges us to grow, not just scientifically, but ethically, emotionally, and philosophically. It asks us to consider our stewardship of Earth, our treatment of each other, our responsibility to future generations. If we are to reach the stars, we must first become the kind of species that deserves to do so, not by building faster rockets, but by building wiser civilizations. And so, we arrive at the end, not of the universe, but of this reflection. And what do we conclude? That there is no final conclusion. That is the point. The mystery is not a gap in knowledge to be filled, but a wellspring of meaning to be drawn from. It is what keeps us moving forward, what keeps our questions sharp, our instruments aimed skyward, our minds open. The universe has no obligation to be understood, and yet, in its quiet unfolding, it invites us again and again to try. Should we ever solve it all? Should the final theory be found, the last particle detected, the deepest dimension mapped? Perhaps then the mystery will simply move deeper, wider, into consciousness, into the nature of reality itself, into questions we haven't yet thought to ask, because that is the nature of mystery. It evolves, it adapts, it survives, and so must we. Let the mystery remain. Let it be the fire that lights the night sky, the silence that sings behind every discovery. Let it remind us that space is not empty, it is alive, with possibility, with wonder, with meaning, and so are we.